Dear colleagues, today we begin our workshop devoted to differential equations and interdisciplinary investigations. Our workshop consists of short cycles of lectures. Each lecture is giving 3 lectures. Some lectures are devoted to more or less abstract fields of mathematics, mainly differential equations. I mean theory of dynamical systems, theory of functional differential equations, and theory of mathematical physics, including kinetic equations. On the other hand, we consider some important applications. I mean applications to numerical methods and simulation, to different problems of plasma physics. We shall consider different models of mathematical medicine and biology, as well as artificial intelligence. For this purpose, we have invited 8 famous mathematicians from different countries. Claude Bardos from Paris, France. Alexander Gorbain from Leicester, United Kingdom. Vyacheslav Grinas from Nizhny Novgorod, Russia. Professor Willy Jäger from famous Heidelberg University, Germany. Professor Lazareva, who is member correspondent of Russian Academy of Sciences. She is professor of our university, Rudan University. Professor Kyun Lee from Changkem National University, South Korea. Professor Volpert, who is working in Lyon University, France, and also in Rudan University, Russia. And Professor Walter from Justus Liebig University, Gießen, Germany. We also invited other mathematicians, mainly young mathematicians, to join our workshop and to listen such lectures, and about 160 persons registered for this workshop. I'm very glad that our young generation is still interested in mathematics and also in interdisciplinary investigations in different applications of mathematics. Maybe you have noticed that our organizing committee consists mainly of very, very young mathematicians, candidate of sciences, doctors of sciences, PhD students, undergraduate students, and all these company organized our workshop. Now I would like to ask one of our lecturers, Professor Willy Jäger, who is at the same time member of our International Scientific Committee in Rudan University, and who is Honorable Professor of Rudan University. I would like to invite him to tell us some words in the frames of opening ceremony, and at last I'll ask member of organizing committee Amina Adhamova to explain you something concerning procedure of our lectures, discussions, and so on. Professor Willy Jäger, please. Your microphone, please. Switch on your microphone.
Now it's working, okay? Dear Professor Skubachevsky, dear Sasha, dear colleagues and friends from Moscow and Russia and from all over the world. I looked at the list of the participants, and it's very impressive that we almost have all continents. We are connected via internet using the platform Teams, hoping that during the next 3 days, we will get a team, despite the distances we have to bridge with the help of modern communication technology. Actually, several of us wanted to participate in these days together in Moscow in the lecture halls of Rudin for the internationally important Congress DFDE, which is one of the trademarks in the field of differential equations and functional equations. Unfortunately, the pandemic has put a damper on our plans. DFDE had to be postponed until next year. But we have the chance to make a virtue out of a necessity, to make this workshop a complete success in this situation, though that it is not just a gap filler, but rather a model for workshops of this kind. This workshop wants to appeal especially to the young generation, for which I believe the chosen theme is particularly suited. Traditional face-to-face conference has a great advantage of providing direct and spontaneous contact, even in conference with a larger number of participants. Setting up personal contacts also in a large set of participants of an internet event is more difficult, but most important, especially for the younger participants. I'm asking them to use all available electronic tools to get into contact also to the senior participants during the workshop and afterwards too, and use the information presented to build bridges for exchange of information and cooperation also in the future. I am sure that the organizers of this workshop are offering their help. You might need to get into direct contact with for instance, with the lecturers. The title of this internet workshop, Differential Equations and Interdisciplinary Investigation, takes up a topic that always has been central in DFDE. The interaction of mathematics and fields, the contents of which can be grasped with mathematical terminology and viewpoints, through which statements can be derived with fixed rules of derivation. Mathematics is a basic cross-sectional discipline which has a universal character. This fact is more and more acknowledged by experts from all disciplines, covering the full spectrum of knowledge and understanding. And especially in time of Corona, where pandemic, where a lot of mathematics is needed, which is not treated very well at the moment. In this workshop, we are focusing on specific tools and its use in interdisciplinary investigation. Differential equations, tools which are in fact key tools of mathematicians involved in application of mathematics. But we are very well advised not to restrict too much to our own tools, but rather include at least differential functional equations and dynamical systems. Let me give an important advice to the younger colleagues. If you are getting involved in an interdisciplinary investigation, do not just take the tools which you know or develop and just look around where you can use and apply them. Please look at first at the challenges arising, analyze at first the situation and find out what appropriate mathematical approach and what are the best tools to solve the given problems. This workshop offers contributions ranging from the theory of dynamical systems to mathematical modeling, analysis, numerical simulation in several topical fields, important as well in research as well for society. Its program reflects perfectly the basic interdisciplinary concept of RUTEN, the host university of this event, integrating research and education and preparing the young generation for the necessary transfer of the result to master the challenges also of society. The pandemic forces also forces us also in research and education to change our approaches. Let us try to use this situation also as a chance and not just as a burden. I wish all of you that you profit from this workshop, which I hope has impacts to new research and activities also in education. My teacher told me, if you are annoyed by a presented result and you do not like it, you better should sit down and improve it. Try to take as much as possible to your own work back. Let me take the chance to thank the organizing team from RUTEN to prepare this event so perfectly. The best thanks for the teams is that we all contribute to make the workshop a complete success under all aspects. Thank you.
Thank you very much. Good morning, dear listeners. About technical part, please note that every day you need to use 3 links. The first one includes first 4 lectures from 10 a.m. till 2 p.m. Moscow time. The second one includes next 4 lectures from 3 p.m. till 7 p.m. Moscow time. And the last one for discussions. If you have questions during a lecture, you can write them in questions and answers. Our moderator will read them to the lecturer at the end of the lecture. All lectures will be recorded. You can watch them later using these links or on YouTube. Now we'll be break till 10 a.m. Moscow time. Thank you.
Dear colleagues, I hope explanations of our member of organizing committee, Amina Adhamova, will be useful for you. And in addition, let me add only, maybe you have noticed already at your screens of computers that a few days ago on August 15, it was birthday of Professor Willy Jäger. More than it was a jubilee of Professor Willy Jäger. And I would like to congratulate him with this day, and from behalf of our organizing committee, and I hope from behalf of all our participants, and I would like to wish him to be healthy, to have new scientific successes, and to thank him for his collaboration with our university and with our mathematical institute, including investigations in so-called pure mathematics and applied mathematics, because this is the same science, mathematics. And let me add also that Professor Jäger was teaching me for interdisciplinary investigations. He invited me many times to Heidelberg, to IWR, Institute for Interdisciplinary Investigations, and other institutions, to different very interesting conferences. Therefore, I would like to tell that Professor Willy Jäger has taught not only me, but our institute, our university, concerning importance of such new trends in science. Really, thank you very much once more. Now we have some break before the first lecture. And our first lecture will be exactly at 10 o'clock Moscow time. It will be lecture of a famous mathematician, Professor Kyung Lee from South Korea. Thank you.
Good morning, dear listeners. We're glad to see you on our workshop. Please again note that during the workshop you can only write questions, and I will read them to the lecturer at the end of the lecture. Our first lecturer is Kyun Lee, professor of Chunam National University, with the lecture Dynamical Systems from Measure Theoretical Viewpoint.
Okay, thank you, Professor Skubacheski, for your invitation. Okay, I'm Connie Lee from Chunam National University in South Korea. First of all, I'm very pleased to give a series of lectures at this workshop on the theory of dynamical systems from measure theoretical viewpoint. Okay. In my first lecture, I will talk about why dynamical systems. And in the second lectures, I am going to talk about differential dynamical systems. And in my final lectures, I will talk about recent trends in dynamical systems from measure theoretical viewpoint. Okay, then let me start with the world of mathematics. Here, two guys are hitting the ball at the same speed with the same force. One ball is small and the other ball is big and huge. Then you can guess the small ball will go further because of the high speed. So Newton expressed this kind of phenomena by mass formula F equal ma. Some other natural phenomena can be expressed by ordinary differential equations or partial differential equations. And then mathematicians develop new theories from this mass formula. And then abstract this theory using axioms, the subject-like dynamical systems, ergodic theory, or algebra and the topology, etc. And also mathematicians develop this abstract theory. Again, from time to time, this kind of abstract theory, abstract mathematics, can be used to describe or explain the natural phenomena. In a sense, world of mathematics is wider than the world of natural phenomena, natural science. So I'd like to say mathematics everywhere and help us to understand the world better. Okay, then what is dynamical system? In Wikipedia, they say dynamical system is a system which describes the time dependence of a point in a phase space. Here, phase space can be a topological space, sometimes can be smooth manifold, measure space, or function space like a Sobolev space. According to the time, we can classify continuous dynamical systems or flows modeled by ordinary differential equations or partial differential equations, or discrete time dynamical systems modeled by differential equations or iterated maps. Between two systems have a close relationship. From the continuous dynamical system, we can derive the discrete dynamical system. Also, from the discrete dynamical system, we can derive the continuous dynamical systems. But I'm going to focus on the continuous dynamical systems in my lecture. So, continuous dynamical systems is modeled by ordinary differential equations or partial differential equations. So let us consider the system of differential equations on the Euclidean space given by system A. X dot equal capital X of X. And the right side is a scalar notation. Left side is vector notation. Then it is not easy to find the exact solution of the given system. If the demand is higher, then it's very difficult, not easy. Of course, even though certain exact solutions can be found, it is more difficult to deduce the long time behavior of the solution curve. For example, solution is periodic, solution of chain recurrent or non-ordering, something like that. It is not easy. But finally, at the end of the 19th century, Henry Poincaré introduced a new method to find the qualitative information of the solution curve without finding the exact solution of the system. So in some sense, he is a pioneer of dynamical systems, Henry Poincaré. How did he make it? How did he make dynamical systems? We suppose the vector field, capital X, is sufficiently smooth so that existence and uniqueness are satisfied. That is, for any initial point x0 in Rn, there is a unique solution x, such that x of 0 is equal to x0. Second, continuous dependence on initial data. It means if you take a too small initial point, then the solution go nearby. Continuous dependence on initial data. With these three conditions, existence and the uniqueness and the continuous dependence on initial data, under these three conditions, the collection of all solutions of the system A can be expressed by one function. I will denote it by phi. Okay, here, phi is a map from Rn to product R to Rn. Phi of x0 of t. If you take x0 point in Rn, and after t second, and it goes to x of t. Here, x of t is the unique solution of the system, such that x of 0 is equal to x0. So the collection of all solutions of the given ordinary differential equations can be expressed by one function phi. Then we can see easily phi is a continuous map because we assumed all solutions are continuous dependence on initial data. That's why the function constructed as above is the continuous function. And also, we see that phi of x0 is equal to x for every point x in Rn because of the existence of the solution through the point. Next, phi of xs comma t equal to phi of x comma s plus t for every time s and t in R. This property comes from the uniqueness of the solution curve of the differential equations. In this case, we say that phi, the function phi is the dynamical system's own Euclidean space induced by the system A. We can abstract these systems on a topological space or on a manifold, on a measure space. So we can get the dynamical system on topological space. Okay, the theory of dynamical systems has application to a wide variety of fields such as physics, biology, chemistry, engineering, economics, medicine, etc. However, the application of such idea was mainly restricted to finite-dimensional dynamical systems that arise in the study of ordinary differential equations. Since the early 1980s, similar techniques have been systematically applied to the infinite-dimensional dynamical systems that arise from the partial differential equations. One would like to study the dynamical behavior of infinite-dimensional dynamical systems using techniques and insight gained from the studies of finite-dimensional dynamical systems. Jäger, Josersel, Thorman, then Henry, they are pioneers in this theory of infinite-dimensional dynamical systems. Then how do they construct the dynamical system from partial differential equation? To see that, let us consider the following reaction diffusion equations on the bounded open set omega in Rn. System E with the Dirichlet boundary condition, U equals 0.
The condition, they have problem.
Huh?
Yeah. The problem for Wi-Fi.
My Wi-Fi?
No, their
Their-
Wi-Fi.
It's okay?
Yeah.
Now, next, okay. So again, so let us consider the following reaction diffusion equation with the Dirichlet boundary condition, where L2 is an element of L2 omega. L2 omega is the L2 integral function from omega to R. That is a Banach space. Then it is very difficult also to find the solution of a given system, and more difficult to deduce the asymptotic behavior of the solution curves. So in the theory of partial differential equations, fundamental problems are well posed in this first. It means the solution of the partial differential equation exists or not, under which condition exists. Second, if it exists, then the solution is unique or not. So the property is continuous dependence on initial data. If a partial differential equation has the property existence of unique solutions and uniqueness and continuous dependence on initial data, then we say that the partial differential equations is well posed. Next classical problem is regularity problem. That means the solution of the partial differential equations are how much regular. Suppose the partial differential reaction differential equation B is well posed. That is, for any initial point used in L2 omega, there is a unique global solution ut of the partial differential B such that U0 equals U0, and the weak solutions depend continuously on initial data. Sometimes in H1 space, strong solution also depend continuously on initial data. Under these conditions, well-posedness conditions, the collection of all solutions of partial differential equations can be expressed one functions as follows also. I'll denote the function by S. So S is a function from L to omega product non-negative real number to L to omega by S of U0. S of U0. U0 is a point in L to omega after t second ut. Here ut is the unique solution of the reaction diffusion of partial differential equation with the initial value U0. We can define, this is well defined by the well-posedness condition. Then we can also show that the function is continuous in each variable because of continuous dependence of initial data. And S of t composite S of S equal to S of t process for non-negative real numbers. In the case of PD, non-negative real numbers, S of 0 is equal to identity. In this case, we say that S is a semi-dynamical system or infinite dimensional dynamical systems on L to omega, induced by PD. Because L to omega is an infinite dimensional Banach space. So S is a dynamical system on infinite dimensional Banach space. So we call S is called the infinite dimensional dynamical systems. We abstract these systems on Banach space. So we get the infinite dimensional dynamical system also on Banach space. So here there is an abstract definition again. A dynamical systems or flow on a topological space is a continuous map with the properties. So dynamical systems in a sense modeled by ordinary differential equation or partial differential equations. So the notion of orbit is the orbit of phi through the point x is the set. Phi of x, t is in R. So the orbit of a dynamical system is an abstract notion of solutions of ordinary differential equations or partial differential equations. So notion of orbit is very important. So let me give us a simple example of dynamical systems induced by ordinary differential equations. Let y equal 1 alpha be a vector field on the plane. Alpha is a real number, and consider the OD on the plane given by this one 1 alpha. Then the vector field is given by the slope is alpha, 1 alpha. So this is the vector field on the plane. We consider the map H on the torus. Is a local, is a chart in some sense given by this function. So this function indicates the horizontal line in the disk turn on the torus in the x-axis direction, and the vertical line in the sphere turn on the torus in the y-axis direction. Okay. We consider vector field on the torus given by x equal h star over y. This is derivative. Then y is a vector field on the torus. So let phi be the flow on the torus induced by this vector field. If alpha is rational, then every orbit of phi is closed. So if you take a point, then every orbit is periodic. And if alpha is irrational, then every orbit is dense on the torus. It's a very simple example of the flow dynamical system induced by the ordinary differential equations. Then what is the main goal of dynamical system? Okay, the main goal of the theory of dynamical system is to understand the long-time behavior of the orbit of the system. Orbit is an abstract notion of the solution curve. What is a long-time behavior of the solution curve? What is a long-time behavior of the orbit of the dynamical system? From topological viewpoint, in this case, we call the subject is topological dynamics. From the geometrical viewpoint, is differential dynamical systems. Understand the long-time behavior of the orbit from method theoretical viewpoint is a measurable dynamics. Numerical viewpoint is a numerical dynamics. Statistical point of view is a statistical dynamics and logarithmic theory, etc. So the goal of dynamical system is to understand the long-time behavior of the orbit. So the notion of orbit is important. So let me recall the orbit more precisely. For any flow, any dynamic corner space, the orbit through the point is the set, satisfying these conditions. What is the meaning of this one? If you take an orbit through the point x, after s second, the point arrives at here, and the t second, the point arrives at here. Then this point, after s plus t second, arrive at here, this point is denoted by phi of x point s plus t. Then 2 points are equal. This is the property of orbit. This concept, this axiom come from the uniqueness of the solution curve of the equations. In differential equation or partial differential equation, also numerical solution is interesting. In general, it is not easy to find the exact solution, so they try to find the numerical solution, pseudo solution. Numerical OD or numerical PD, they try to find the numerical solution. So solution corresponds to orbit in dynamical system. Then numerical solution corresponds to the pseudo orbit in dynamical systems. Okay, what is pseudo orbit? We are going to take a point x0 in the phase space. After t0 second, arrive at this point and jump. We allow the error, delta error, truncation error or error. We allow from this point after t1 second, arrive at here and jump. Also, we allow delta error from this point around the real trajectory, real orbit, move around t2 second and arrive at this point and jump to x3 within a delta neighborhood. This also negatively x minus 1 after t minus 1 arrive at this point. We allow uniform error. This is the delta pseudo orbit. We can express this one by xi. Xi is the collection of pairs xi, ti. Xi is an x0, x2, x3. This is a point in phase space. And the ti is the time, has a lower bound. For convenience, ti is bigger than 1, just. And the distance between 2 points, xi, ti after ti second, and the distance between 2 points. Here, this point is p x2 t2, and the distance between p x2 t2 and x3 is less than this delta. In this case, we say that xi is a delta pseudo orbit. So this concept is motivated by numerical solution. In the numerical analysis, we try to find the numerical solution. If nearby numerical solution, pseudo solution, if there is a real solution, it is very good system. So we can we have a question. Near this kind of a pseudo orbit, is there a real orbit or not? In other sense, near the numerical solution, is there a real solution or not? If it is satisfied, then we say that has the shadowing property. So let me explain shadowing property. Okay, here is the delta pseudo orbit. In the neighborhood, if the neighborhood of the delta pseudo orbit, if there is a real orbit through the point, some point, if there is a real orbit, in the case, we say that the system, OD or PD or dynamical system, has the shadowing property. So, yeah, formally we can say a system, a flow, or dynamical system, or partial differential equation, or ordinary differential equation has the shadowing property implies. For any epsilon, there is delta, and delta should orbit can be epsilon shadowed by real orbit. That is increasing Homeo, blah, blah. This is just ignore the speed. So we are concerned about the long time behavior. So if orbit, the speed is different, it doesn't matter. So the function here, h, control the speed. Control the speed. So shadowing property implies give a good relationship between orbit and pseudo orbit. So real solution between real solution and numerical solution. If you take a numerical solution nearby, if there is a real solution, then we say the system has the shadowing property. For example, in PD, partial differential equations, Chaffee-Infante equation, in the case of Chaffee-Infante equations, Grover tractor, if you restrict the system on the Grover tractor, then the system has the shadowing property. So it is a good question. When the system has the shadowing property, next, in the theory of dynamical system, one of the important and concept is expansivity. Let me introduce what is the system is expansive. To do that, let capital C be the set of continuous functions, and gamma delta phi of x is the set of y, such that the distance between 2 points less than delta. Here, this is the orbit through the point x. This is the orbit through the point y. Ct is just a continuous function. So this is the control the speed. In the flow case, nearby two orbit, the speed can different. But using the function c, we can control the speed. So if what is this one? This set is called by dynamic delta ball. I'm going to call this ball, this set is a dynamic delta ball of x. It means the set over point y go together within a delta neighborhood. So dynamic delta ball is the set of y go together. So, right? In this case, Lopez, Bowen, and Peter Walters in the early 1970s, they introduced the notion of expansive flow. Flow is expansive in price. For any epsilon, there is delta, such that dynamic delta ball is contained epsilon arc. Epsilon arc. This is the epsilon arc. This is the set of phi of x, comma t. T belongs to minus epsilon to epsilon through the point x, epsilon arc. Every dynamic delta ball belongs to epsilon arc through the point x. In the case with that phi is expansive. In some sense, this concept is strong, but very useful and important terminology in the theory of dynamical systems, also other field. What is the geometric meaning of expansivity, roughly speaking? So here is the orbit through the point x and the delta neighborhood of the orbit. If you take a point y outside of the orbit, then the orbit is out of the neighborhood, go out neighborhood sometimes. Similarly, if you take a point z not in the orbit through the point x, then the orbit through the point z also go out, is out of the neighborhood. only epsilon arc, red colored curve. If you take a point in here, can go inside, go together. Only inside here. This concept of expansiveness is introduced by Rufus Bowen and Peter Walters in early 1970s. In the theory of dynamical system, also important one of the important concepts is stability. Is a fundamental and basic concept. We say that a flow or dynamical system is topologically stable, implies for any epsilon there is delta such that in the small perturbed system, psi is C0 perturbed system. So it's very strong perturbation, just a continuous perturbation. Then there is continuous map and the continuous alpha reparameterization function such that H send to perturbed orbit of the perturbed system to the orbit of the original system. I'm going to explain it by figure, it's better. Okay, here is the space M, phase space, and dynamic flow, phi, OD or PD, doesn't matter. The stability, topological stability means we perturb. Psi is a small perturbation of phi. Then, if you take a point and the orbit through the point, this is the psi orbit at x through the point x. This is psi orbit. Then there is continuous map H. Here is H of x. This is the phi orbit through the point of hx. Then the map H send this orbit to this orbit. If we take another point also orbit, also by H, this orbit send to this orbit. This is a kind of stability. So in some literature, H is called by semi-conjugacy. So topologically stable means under the C0 perturbation, there is a continuous map H which send psi orbit to phi orbit. This is the notion of topological stability. So see, in the theory of dynamical systems, when the system is stable is one of the fundamental questions, of course. In the theory of infinite dimensional dynamical system, also. So recently we are working on the also reaction in PD, reaction diffusion equation. In the case of reaction diffusion equations, we perturb the domain or nonlinear part. C1 perturbation usually. Sometimes repulsive perturbation. Then how much dynamics are preserved on the small perturbation. This is a kind of stability problems. So let me introduce very fundamental theorem by Peter Walters. The theorem implies that if a flow is expansive and has the shadowing property, it is topologically stable. In this direction, I'm going to give a lecture in more detail tomorrow. So today, okay, let me summarize today's first lecture. the collection of solutions of well-posed ordinary differential equations or partial differential equations can be expressed by one function. We know the collection of solutions of well-posed OD or PD can be expressed by one function. We abstract the systems on topological space, sometimes differential manifold, or measure spaces, Banach space or Sobolev space. Here in the theory of differential equations, solution, the notion of solution is important. Solution corresponds to here orbit. So the solution in differential equations correspond to orbit in dynamical systems. Also, numerical solutions in differential equations correspond to the huge orbit of the dynamical systems. So, the main goal of the theory of dynamical system is to understand, again, long time behavior of the orbit of the system from topological viewpoint or geometrical viewpoint or measure theoretical viewpoint or numerical viewpoint and the statistical viewpoint and so on. Okay, for the fundamental theory of dynamical systems, let me introduce two books. First one is written by Maurice Hirsch and Smale. For the graduate and the undergraduate student, let me introduce this book, Hirsch and Smale. The title is Differential Equations, Dynamical Systems, and the Linear Algebra. For the infinite dimensional dynamical system, I think is for the graduate student. Infinite dimensional dynamical systems, an introduction to dissipative parabolic PDEs and the theory of Grover attractors, written by James Robinson in the University of Warwick. Okay, this is the end of my first lecture. Thank you for listening.
Thank you for your lecture. Seems like everything was clear because there are no questions. Maybe there will be later. But
can I ask a question?
Yes, sure.
Professor Lee, I'm very much interested also in dynamical system having several time scales.
Time scale. Yeah.
Let me give a simple example because we are looking a lot of in medicine. You have heartbeat, high frequency, and you have blood flow. And a lot of sicknesses are long time properties of the flow. That means this is PDE and complicated, but in principle, how can one separate the effect of this rapidly oscillatory, which is characterized by the heartbeat, and the long time evolution of some others, which is inside the dynamical system? Is there already done something in this direction?
Okay, frankly speaking, I'm not familiar with the time scale dynamics, just that is combination of the discrete dynamical system and the continuous dynamical systems. So the derivative and everything are slightly different. They we need the time scale analysis. The time scale dynamics, as far as I know, time scale dynamics is initiated by Hilger. Am I right? You're talking about that timescale dynamics, right?
There are a lot of contributions, therefore I don't.
Yes. So I'm sorry, I am not familiar with the timescale dynamics.
I'm
Just
asking that.
Combination, combine. It's a middle, discrete dynamical system and the continuous dynamical system and timescale dynamical systems.
But you had in the beginning this, you had these shooting trajectories. It could be related to this because the shooting trajectories, the size of the shoot would be in small time scales.
Yes.
In the rapidly, and the others is the long time situation. That's why I'm asking that, because it would be a natural approach to look at things.
I see. Yes, very interesting. But timescale dynamics, yes, in the a little bit. I know just the definition and some, but I'm not. I'm sorry. I don't know much about
no, that's
timescale
very
dynamics.
much known about this but it's urgently needed for, especially with this approach which you said you use shooting trajectories.
Yes. Thank you. So maybe left side in your screen, you can see my email address. So
okay,
contact me.
if you have, okay, fine. Thank you.
Thank you very much.
Thank you for your question, Professor Jäger. And again, thank you for your lecture, Professor Lee. I think we can make a break for 13 minutes till 11 a.m. Moscow time. So,
thank you.
Thank you again.
Hello? Or now, can you hear me now? Can you hear me now? Can you hear me on the...
Yes, Professor Jäger, we can hear you.
Now, because it was switched off. Okay, because it's a very small mark here only. Okay. Okay, then it's everything is okay with me.
Yes, now the next lecture will be given by Professor Willy Jäger, the professor of Rupert Karl University of Heidelberg. And his lecture will be, the topic of his lecture is, can mathematics help to understand and control COVID-19?
Wait a moment, I have to open it.
And today it will be the first lecture of the cycle. Professor Jäger, please.
Okay, thank you very much that I have the chance to talk about a topic which troubles us a lot at the moment, and where I think, which we will find soon in a statement on the next page, without mathematics we will be not able to manage this crisis on quite several reasons. Here you see up on the left-hand side this famous virus with the spike protein. And let's be concerned in the next lectures with the problem, can mathematics help to overcome the corona pandemic? Stopping the pandemic without mathematical and computational science is a mission impossible. I really can say that, and I hope I can convince you during this lecture that I'm correct. And behind that is clearly at first mathematical modeling, which we have to all of the unknown processes. So this corona pandemic has a damaging impact of like a meteorite on mankind, because it doesn't just hit our health, it hits our whole economy. And all over, when you want to take care of this lateral damage, we need essentially also a lot of mathematics. I quote our chancellor still now, Merkel. She said the situation is serious, take it seriously too. Mathematicians are challenged to join teams of scientists from a wide range of disciplines in order to cope with this shocking event and the threat of the virus also after the pandemic. Substantial contributions are needed from mathematical and computational science in areas affected by the consequences of the pandemic, and where the measures to be taken should be based on their support. I hope that I can convince you that what is done now at the moment is not using the good mathematics, and we have to get involved more with these problems. Epidemiologists are relying on mathematical models, which they sometimes don't tell us, and they are very old-fashioned, to help policymakers to get ahead of the COVID-19 pandemic. But the leap from equations to decisions is a long one. And the problem is to find the equation, and most of them are partial differential equations or functional differential equations, what we consider. I show you now the picture at the moment, how many we have had on many cases. August 17, we had total cases more than 20 millions, 22 millions, recovered about 14 millions, and deaths 775,000. 100,000 deaf people. And it really influences us a lot also in science, and we have to show that we can contribute, and I think we can. Now let me look at first how it developed, because this is already an important situation. It started, the SARS viruses, already we had infections starting in 2003 in East Asia, known as a severe acute respiratory syndrome, and it causes damage, and which causes damages and dysfunction of the lung. But the now one, it started in December, as you know, and it developed. They didn't know how to call it at all in the beginning, but already in January 30th, WHO, the World Health Organization, declared the outbreak a public health emergency of internal concern. In March 11, WHO classified the infection COVID-19 as a pandemic, developed globally to a serious, almost unprecedented pandemic. Now we have at the moment, on August 70, almost 20 million COVID cases in 188 countries. And I mentioned it already before, more than 775,000 deaths. Now, enormous qualitative and quantitative consequential damages was, and it's difficult to assess and can only be remediated with greatest effort, if at all, only in the long term, provided that the pandemic can be brought under control quickly enough. Tackling the pandemic requires full commitment of all sectors of society, also of the sciences, in particular of mathematical and computational science. The aim of this lecture is to stimulate and interest and cooperation in the transfer from mathematics to coping with numerous challenges. Needed are, for instance, concepts to tools from several fields of mathematics, certainly differential equation, but not exclusively. Current information and basic facts concerning on the virus and the pandemic. This is a very difficult problem because in order to make mathematical models, one has to know about the behavior of these terrible beasts. The mathematician, I quote now Blaise Pascal, the mathematicians who are only mathematicians think right, but only on condition that all things are explained to them by definition and principles. Otherwise, they are limited. I do not share his opinion now, and unbearable, but they think correctly only when very clear principles are involved. It's hard critics, but it's very important to realize we not can assume that we know the equations. We have to find them, and in order to find the models, we need a lot of knowledge about possible models, and there all the input of function analysis, of analysis, nonlinear, also numerics and statistic and stochastic comes in. Otherwise, you cannot solve this problem, finding good models for the problems which we have to solve. Typical features of the dynamics of SARS-CoV-2 and COVID-19. The first part is the virus, and the second part is the disease. As in all infections, structured population of interacting agents have to be considered. Pathogens, hosts, vectors growing and spreading in space and time. Dynamical systems describing the evolution of this system in space, in time, but also in state space, because we have a structured population, age, for instance, or health properties known before. And if you look at the equations or models which are around now, they are far off from what we really need. In case of COVID-12, we assume that the transmission is just by human hosts, which is not absolutely clear. But at the moment it's assumed. In particular, interactions have to be taken into account between individual agents, case of the virus disease, also the evolution inside of the single host, changing also the features and interaction which up to now, if at all, can at most only be grasped qualitatively, but not quantitatively. For instance, you remember, you hear always in this use that a lot of people who are attacked by the virus don't show symptoms. That's a very complicated situation, and one of the most dangerous is that SARS-CoV-2 is a hidden and unpredictable virus. Essential research aim is understanding and controlling its growth and spread in a single cell, in the organisms and in the populations. I have these three topics in the three following chapters, but I have to give here an introduction in general. The course of this disease is very different sometimes from what is known, and sometimes very surprising. I have had all the time very good relations to the medical doctors and intensive care station. Always they said, we saw something new which we have not seen before. I have to tell you, I'm very much involved in this disease because it's essentially a virus sepsis, and we are studying sepsis, which I will explain later, already for 5-6 years with mathematical modeling. And now let me see what comes next. Main features of the virus. You know that we have, it's very airborne transmission is dominant route for the spread, but not only. You have two kinds of spreading through the air. It's by droplets, and it's by coughing, and also by contact. But which is very, very important and very much not in the models which are around up to now is the fact that we have super spreading, which we know already from HIV studies. There is, everyone maybe remembers that HIV started in California mainly to a super spreader who was in the staff of an airplane coming from Asia. The hidden unpredictable virus. The incubation time of this varies enormously of the virus. It's 1 to 14 days when you get into contact, and then before you get infectious as an exposed one, and this is already a problem. All the models which I looked at, which are used in prediction also for the measures be taken by our governments, don't include anything, things like that. Infected might be just carriers, also not develop many antibodies. Virus characteristic antibodies are sufficient for having had an infection, but not necessary. The infected can be without symptoms. Unpredictable. SARS-CoV-2 differs in many aspects to its SARS relatives. A really new virus causing an unknown disease with many surprises also to the experts in the intensive care stations. Up to date, there is not yet success in identifying the infection in a larger population. Better test strategy may help to reduce the uncertainties. We have now at the moment some kind of really terrible mistakes in testing in Germany, which creates a new small wave, at least in our country. Uncertainties in all topics of the virus profiles which are crucial in understanding the evolution of this population and this disease. I show you probably on the next page a list of properties listed by the Koch Institute, which is responsible for controlling these epidemics in Germany. I just want to show you, read it by yourself, what everything of this red part can be a part of a modeling, and it's, you see already on the number of different topics which are already acknowledged as important for the disease by our main institution, medical institution in Germany. And I just left a few which might be not necessary. All the others are, you can see, are important. And especially is the problem not a possibility of vaccination. There is now hope, and I hope it's really will be realized in Russia to have a vaccine. But it still, I think, has to be tested more and see what is the outcome. And I hope, because we only can hope, that vaccination works. It does not work for, as you know, for HIV virus. SARS-CoV-2 starts as its relative as a disease of the respiratory system, in particular the lung, leading to critical inflammation and spreading in the whole body. And what is very important, and this we studied for a long time with mathematical models, it creates essentially lack of oxygen and hypoxia. That's missing oxygen in all over. That means also missing energy support by the respiration based on oxygen. There are other respirations, but this part is missing. And the disposal of CO2 is also disturbed. And And there I found already something interesting. There's almost nothing studied mathematical modeling or something look at how CO2, which stays in the body, is negative for the body. I asked medical doctors and even they could not tell me. Sepsis is what I said an important part because sepsis is a lifelong threat, a life-threatening systemic organ dysfunction due to dysregulated body response to an infection. What is a response of the body? That's the immune system reacts with an inflammation, and this is positive. And usually we were looking just on inflammation started by bacteria, fungi, and parasites, but not viruses, because they only decided to take viruses just 2 years ago to a cause of this disease, which leads to multiple organ failure and has a lot more. Has had a lot more of deaths. Only in 2016 in Germany, we had 77,000 people dying from sepsis. But now we have the virus sepsis in addition. Hypoxia, that's a deficit in supply with oxygen, and as a consequence also the deficit in energy supply, critical for the whole organism as a system. As in case of COVID-19, there's especially to be seen that the influence of the missing oxygen influences essentially the blood system. The particles in blood system. Suddenly we have an enormous, even life-threatening effects of superclotting, which in normal sepsis only came later, in multiple infarcts in organs. And this has been studied, clotting processes have been studied also with mathematics. What are the challenges? Medical challenges is clearly it's for the public health, and I think I can leave it to your own experience how important this it is to handle this pandemic also for our medical system. Biomedical and technological, developing tests and antibody tests are used at the moment. Preferable would be antigen tests, because antibody tests are not directly identifying the virus, because only the reaction if you had virus. And this needs a lot of studies in mathematics, and I will talk about this later. Also the vaccine. So problems of efficiency, immunity, and side effects. There you also can do mathematical support, and medication. That's classically already, we have been in drug design already a long time, and especially find checkpoints in the dynamics of this beast, where you can stop its growth and its spread. And there we have around already mathematical modeling very successful to help. Measures have to be taken to control the corona pandemic, changing life in all aspects, causing a huge lateral damage. Restrictive regulation and supportive measures are necessary, but they have to be justified. A quantitative risk management approach is necessary, requiring mathematical predictive modeling of the changes of the system and the effects of the measures. One of my former students just told me on his birthday card that what he is working with one of the largest insurance companies, Münchner Rückversicherung. What does he do? He studies risk analysis, risk caused by the pandemics for the insurance companies. But we also have to see lawyers in the meantime have to judge if someone doesn't keep the restriction, what does it mean for the society? They also need what is the influence of measurements, economical, financial, and I will quote shortly afterwards a comment of in another connection of one of the bankers. Political and social and cultural, religious, everything is really very much depending on the decisions How can we control and how much can we control these epidemics? Let me just go to the scientific part. Here we need to cooperate interdisciplinary network with our professional competence to better understand the dynamics of the virus and the pandemic and their consequences, and to control them with the appropriate measures. Mathematics and computational science are particularly challenged to contribute, especially based on data and empirical knowledge about the virus and the pandemic. We have to reduce the uncertainties. That's very important for our whole society, and mathematics cannot stay just in their offices and prove theorems. They really have to help with their knowledge, also with new theorems, what happens outside in this terrible situation. Now let me just collect some mathematical topics. Data collection and analysis. Here we have really also the influence of, we have a colleague who discusses about contribution to AI, and it would be very necessary that it gets more involved. I ask here the question, where are so far a substantial direct contribution of machine learning to the knowledge on the virus and pandemic? I cannot see that. It's maybe in some kinds in order to determine the structure of the genome, but this has been done already for bioinformatics, but we have to use this more in order to get more about the knowledge. Now, what topics in modeling, mathematical modeling and analysis and numerics of the model systems are challenged? Calibration, simulation, validation of the results. We also have to optimize because you have different kind to react. You can use the tools of digital experiments in order to find out, watch out. If you take this method, you change something in the system and that place. And this is not done to the extent which is needed. So processes to be treated run on different scales. We really have to consider the virus on the molecular, cellular, tissue, organ, and organism scales, and in populations. Include a large spectrum of different types, especially different types, biophysics, biochemistry, biomechanics, and fluid mechanics. They lead also discrete, continuous, stochastic, and deterministic systems, and on complex geometric structures. Often these structures depend on their state. This is coming up in the full complexity, but we have to do that, otherwise we do not fulfill our job as contribute as mathematicians as good as we can. Okay, let me give some examples. Where I have to. It's a prognostic strategy of control of the evolution of the disease in infected individuals in the population. Quantitative approaches for design, production, and application of tests, vaccines, therapies, and medication. But to figure out all the mysteries of SARS-CoV-2 will take years of theoretical, experimental, and mathematical computational work. Every breakfast, if I look at the information which I get from my medical friends, today I got the information. The virus influences are apoptosis of the cells. It takes care of that the cells do not die too early before they have reproduced its material. And that's, you find every day another new surprise. Now what tools are needed? Data analysis, statistical machine learning in time, space, and state space. Discrete and continuous stochastic and deterministic modeling of physical, chemical, biological, medical, technological, and social processes, complex multi-scale media with nonlinear interactions. system reduction and methods bridging scale methods to reduce the complexity. We cannot solve these problems in the full complexity. We have to reduce them and make it accessible, make them accessible to a possible way. And the effective system, we have to do systems reduction, and we have to do systems reduction and find new quantitative, more accessible descriptions to describe, for instance, the activity of the virus infiltrating the organs, attaching to the body cells, penetrating the cell membrane, proliferation of virus protein inside the cell, growth and spread of inflammation and influence on the whole system of organs in an individual host, blood clotting, and life-threatening infarcts in the organs, which is a very important part because it's one of the main problems that medical people have at the moment. And they are different than that what we have done before. Growth and spread of pandemic in structured population, including the dynamics of the virus in the host, the mobility and the social behavior of the population, leading, for instance, to super spreading of the infection. This was a more general overview. Now I go and see what we can say about the virus inside essentially in a cell. And first, I give you some biological facts. The SARS-CoV-2 is one of the SARS viruses. It's a viral, it has a viral RNA genome, it can, but it's not, a virus is not a living system. It can only multiply using living systems. It consists, as you will see, mainly of 3 parts, and which I show afterwards. And they have a genome, which is very well known in the meantime, and they differ not a lot. And the problem is how the difference in the genome is related then to their reactions in order to explain the pathophysiology of the severe COVID-19 disease. It's necessary to understand how are the differences in this genomic structure in order to be aware, to maybe help to avoid the spreading of the virus and the disease. And as I said before, we want to understand this virus as creator of virus sepsis. The virus starts with mainly in people, it could be also something different, but it's a main thing which we know. It causes a viral pneumonia with serious features different from that which we know from the known SRS viruses. Essentially, it penetrates in the lung, and you see down here, you see here on the left-hand side, the structure where it gets terrible. It destroys this alveolar situation, it destroys the alveolar and the blood vessels, where there is an exchange of oxygen and CO2, which is necessary for our survival. And so you see down here the complicated structures, which we have to understand how they are changed by the virus in order to know its influence on our supply with oxygen and our balance with CO2. And now here you see it more specific, and then I can already tell you what do we know, what is the mathematics which we are interested in. You see here the alveolar, one alveoli, and they get in the O2, and here you have a capillary, and you see the change from blue to red, and that means the oxygen has already penetrated over and been loaded to the particles in the blood. And now if the virus attacks it, here on the left again you see the cross section of that, and here you see it enlarged, and the virus destroys these epithelial cells, which are covering the alveoli and covering also the vessel wall. And then the permeability changes, and sometimes they are destroyed. The capillary system is totally destroyed, and the functioning of the lung is influenced. And this picture you see on the left-hand side, you see the viruses that are the smaller black ones. One I circled with a red circle, and here you see a cell in the left corner, and it's very interesting. The structure of the cell changes under the influence of the attack of the virus, and I will comment that more than afterwards. But this structural change is very important for the virus because they can attach more. And the aim of the virus is to go inside the cell, where they multiply with the mechanism of the cells, multiply their proteins, which afterwards are put together again to a virus particle, which leaves this leaves the cell. But what is very important, it's in general to say, the attack of the virus goes to the epithelials that are small layers on the surfaces, for instance, of the alveoli, or in the case of blood vessels, one calls them endothelials, and they are attacked. And why are they so nicely attacked? They're because this virus likes something which is called ACE, is an enzyme which is used for controlling our blood pressure, and especially that means the effect is not so nice for people who have high pressures and blood pressures, because they have a lot of receptors on their cells which can where the virus can attach. Hypoxia, that's the influence, inflammation, and a cytokine storm. This is really the first really serious attack. Structural changes, properties and function are changed by the miss of oxygen, because oxygen is needed in almost all processes we have. Cells are destroyed, blood microcirculation is damaged, hypoxia and inflammation are developing, because at least the body reacts, the immune system interacts and signals to the rest of the body there is an infection coming, and this is very dramatic because we really have the lung, which is very important for the oxygen supply, which is attacked first, and I mentioned that already before. So, and the clinical reports is very important for us. That mainly thing is a cytokine storm. Cytokine storm means also signaling which is produced is really in a form of a storm, having different kind of effects. This picture shows you some of them. There are a lot of cytokines, and each one has receptors on certain cells, and the system is very complicated, but it has, as a consequence, if you have this dysfunctioning, you get endothelial layers are dysfunctioning, the surfaces of the blood vessels. The inflammatory response is getting different. You can have two kinds of response. First is it explodes, the inflammation cannot be stopped. But it also can lead to the fact that it is stopped, because very often is such cytokines or all substances which you have controlling are not always just anti, but also pro, not only pro, but anti-inflammatory. Now you see the virus structure. You see 3 parts, but I have to look a little bit on my time. You have the spikes, and on the right-hand side you see the image of a virus again. And the genome really has been studied. It's very well known. It has 29,903 base points, and this is not a problem. We have very much knowledge about that in the meantime. And also it's analyzed with the different, the genome has been very carefully analyzed for the different viruses in order to see SARS related viruses, where COVID is one, SARS is created by one of them, and we have to know the difference. But it's already quite well understood. And you also have to see it's not stable all the time. And now you see the important part is a spike protein, spike glycoprotein, because it's important for attaching to the vessel wall, and it's very well studied. And here is something which I cannot very much explain, but it's really true. Here it's the structure of this complex is of high interest. Not every formation of the molecules is possible, and if you look at the restrictions, then you can say, and it is used, especially by Bob Penner. I'm sorry, I wrote him wrong here. The striking theorem is that the Riemann-Moduli space of a surface F of genus G with R boundary components is combinatorially isomorphic with the RNA moduli space up to homotopy. Therefore, here, studying this virus, the structure of this glycoprotein is very closely related to really high-level geometry. And the cycle of the virus. The virus has to go inside. You see here, up here, this attaches, and then it hooks on and goes inside. And inside it multiplies. Here you have the processes. And I have to hurry up a little bit. You see here it goes in, opens up, and the process, the protein is multiplied, and then it comes together again, forms a hull, and has to go out again. It's this process we have to try to model, and we did that partially. And what is very interesting, we have to find checkpoints where we can block this dynamics. And we are on a good line using also methods of differential equations, but also, as I told you, also geometric methods. Now let me show you. Now let me just, here, I mentioned that already earlier. There are special structures which are conserved in all these glycoproteins. It's up here, it's a hydrogen bond bifurcated bond, which is in a backbone, and you cannot move these guys very well, but around that things can move. And the problem is find out this three-dimensional structure and see from protein database and try to find out how can you deform these structures, which should be done mainly by molecular dynamics, but at the moment it's too complicated yet, but using also problems of variational of energies, which are closely related to these bonds. One can do mathematics and reduce the information, get more information on the structure. In fact, Bob Penner could identify the critical points where there can be hooks on. You see them marked in a lot of balls which mark as the molecules, and this red and orange part indicates the spaces where things can hook on. And if you know that, you can try to put obstacles that it can happen. Here you see again this situation, and here you have the spike protein, and you have here a hole. And here you have the image of the enzyme 2, and you can see the red part moving in this hole. And I did this with just by moving geometrically, but one would have to do it as a huge system of ordinary differential equations, doing molecular dynamics in order to get this done. Here you have one example where we did it in a different case, such a molecular dynamics system. It's a huge system of ordinary differential equations with all kinds of forces acting between the molecules. And what you see here is movement in a myosin, of a part of the myosin which interacts with the actin in muscles. And this is what we have to do also for this huge system of what we did, and very successfully, we did the studies the entering part of. Wait a moment. What is going on? It stopped. Sorry. It stopped. Can you see me?
Yes, Professor Jäger, can you please restart your demonstration on the screen?
What happened? The demonstration restart. I can try to restart it. Wait a moment. Okay, I go here. And let me just restart. What happened? Here, okay. You see this, you see the structure of the vessel wall. It's a bilayer of molecules, and one has to set up an energy functional for this.
Excuse me, Professor Jäger, cannot see
you cannot
the
see
presentation. Yes.
What happened? Wait a moment. I don't know what happened. Sorry. Wait a moment. I try to start it again. Wait a moment. Can you see it now?
Yes, thank you. We can see.
Oh, sorry, I don't know what happened. The system broke down. And you write down the energy functional for this for the mechanical energy of this surface, and you have in the mean curvature, Gaussian curvature, and some parameters describing the rigidity, and a functional which cites the chemical energy. And then you get a complex situation of such an energy functional. You see here the mean curvature, Gaussian curvature, some function which depend on the chemistry, and here's the chemical potential. But we took a very simple situation, not really a full chemical system, but we can simulate now we could simulate the entrance of a HIV virus. It goes now. You see the cell interior is up, and the virus comes from the underground, from down there. And we could show budding and of this. And it's very complicated system. In fact, it's the Wilmer equations are a part of it, numerically as analytically. Then it's a molecular, the release and the replication. I also had a PhD thesis describing all of this huge system of multiplication. It's a cascade of production of proteins, and and what my student did, she also analyzed, looked at this huge system where are critical points in this dynamics. If we stop there the process, the whole process of this viral replication is stopped. I have to hurry up, and therefore I only can show you. This is a scheme of this huge system. It's mainly stochastic and deterministic. ODEs, no spatial effects are included. We have to put a lot on this medical part, because I'm not so sure if we're really successful with vaccines so well as we should. In the ARV virus, we have no vaccine up to now, but we have medicaments. And this is the budding going to the other side. So, okay. Here I want to finally show you something, because it's interesting that the virus changes all, and also hypoxia changes also properties of the vessel, the particles, and here of the cells. This kind you saw already before, but this is now a microscopic image of a red blood cell, and it has totally been deformed by the virus, which is an advantage. The surface area is enlarged, and you see these little spots are viruses. And you see this spiky production, which I can show you in the other lectures, comes mainly from hypoxic situation. And let me finish this today, because I did not show you very much on equations, but I show you now a picture. If you look at this, it's clear what kind of mathematics you need there. You have porous media. Porous media, complex porous media, interaction with particles in the porous media, and the porous media structure here is poroelastic. It's not fixed. It's clear. It's products. And what is the problem which we want to solve? We want to study, and we do it already in other situations. Also for this virus, we want to study the situation locally. On the microscopic level, derive some equations on the micro level, on the cellular level, which we can scale up to a limit, which we can use for an more effective model, because finally the answers which we want to get are on the macroscopic level and not on the level of the microscopic, but we have to take all these changes up to the level of organs and of the whole body. And finally, if we want to use it in population, also up to the level of the population. This is still the action of the B cells, but I may skip it here because I will talk this afterwards. Anyhow, once more, we also were involved in constructing the antibody tests, which I wanted to show finally, and also involved also in the vaccine development, because a vaccine clearly has also to take into account the properties of the cell, of the micro properties of the micro properties of the virus, and also of the immune cells, essentially B cells and T cells. I just want to mention here that I think we have to really get also to this kind to models of this immune system, part of the immune system, because at the moment we rely on a theory which was excellent by George Bell, which was in the 1970 to 1980, and we need more specific knowledge because we have more knowledge on the biological side. So here it's the end of this lecture. Sorry, I took a little bit longer.
Thank you very much, Professor Jäger. And now our audience has some questions. Please, Professor Jäger, do you have any predictions when the disease will end? What will be the consequences of the pandemic?
Wait a moment. So you asked the question how people behave. Okay, that's very important. When it started, I followed it from the beginning very carefully because I immediately saw it's a virus sepsis and that hypoxia, which I'm really specialized on that from mathematical modeling of that. I've solved quite a large part already if people would have kept the restrictions which are necessary. And therefore, probably we will have not before next year a really reliable vaccine in the following sense. You have one now introduced in Russia, but you left out the test period. And this, if it succeeds, great, very happy. But we also have to take into account it could happen that it does not succeed fully. Then it's not good. I would say maybe, I hope that the beginning of spring or in the spring next year we are in a better shape. Only if and only if people keep the restriction. We have super spreaders. Our problem are the super spreading people. If you cannot control them, let's say travel in all or directions for Mallorca, no. If you look at the number which Bavaria had, it was mainly coming from a ski resort in Austria. That's my answer, which otherwise it's not clear.
Thank you.
More questions?
Yes, the next question is, can COVID-19 be mathematically modeled by semi-Markov processes in probability theory?
First of all, I think if you start, usually if you start, you have always stochastic processes on each level. But we cannot afford to keep on this level. And we have to pass to effective equations, which usually are no longer stochastic equation because they are very complicated to compute. And we did similar things, for instance, in a very simple situation, not for the virus, but it's a similar aspect is usually you have a lot of knowledge already in what happens inside the cell, and don't consider this as stochastic. Also, you can consider this stochastic. But if the cell is like a chemotactic moving somewhere, then it's a very important stochastic outside, the movement of this particle in environment. And we did this very careful. And the outcome is a huge hereditary stochastic system with hereditary parts, which we tried finally also to approximate this is very challenging topics, and I think it has to be done because there are effects, stochastic effects, which we have to take into account, and you cannot get them just by deterministic upscaled equations which you do not know. Also, it's very important, these equations usually have memory terms, functional terms, maybe also in space, but especially in time. If who is interested, I can give him a copy of this PhD thesis. Was probably 2 years ago, 3 years ago. On the chemotaxis of E. coli and the viruses, all these immune cells are going. They move chemotactically too. That's the same type of problem.
Thank you very much. And the next question is there a possibility to protect these investigations from falsification of the statistical data?
Excuse me?
Is there a possibility to protect these investigations from falsification? Yes.
I don't know what you mean by protect. Oh, you mean you will test it by data. All these equations, every equation has finally been tested by real data. That's absolute. Validation is one part of it. It's not easy. And we do it in all steps. We try to get data in order to validate them, if they are there, because very often it's not easy. One thing which we did, it's very interesting, which I want to mention. There are something in the equations which you probably will never have a chance to test directly by data, but indirectly. You can use, in order to determine some parameters, for instance, in systems of the equations, and in fact we did it for the virus penetrating, we did that. We used molecular dynamics to determine from another model, to determine the relations between the coefficients of these equations and the chemical concentrations. And then you put this computer experiment data in it and get a system, and you have leftover parameters which you validate if they can be determined by macroscopic observation. This is, I think, a very, very important step and has to be used more often, because we cannot everything test directly by data. It's not possible.
Thank you very much, Professor Jäger. I guess we should make a small break before your next lecture.
I have to. Will we stay online? No. Do you stay me online here, or do we close down first?
You can close down first.
No. You can leave it. I can just switch the go to the other topic. Okay.
Okay.
I have to go first. A second. I come back in a second. Can you still see?
Not yet.
Can you see the slide?
No, Professor Jäger.
No, then I have to do it once more. In a moment. Now? Can you see it now?
Yes, we can see it. Thank you.
Then because here. I only have to see if it's the correct path. No.
Dear listeners, so Professor Jäger will give us the second lecture of his cycle on the topic of can mathematics help to understand and control COVID-19.
So may I continue, and then we go now and see what can we do now, which processes can we do? Look now at the in the host. As we said already before, the infection is an infection of the lung first, and impacts. Virus infection of the lung leads to reduction of oxygen supply for the organism locally and in the whole body. Oh, there's hypoxia initiates local inflammation in the lung, infection processes and the inflammatory collateral damages causes cell dysfunction and death of the lung tissue. That this death of the lung tissue creates also particles which are going to the rest of the body and can create all over infarcts. And this was one thing which was a catastrophe for the internal medical people, intensive care people, because they did not expect that. Waste products and necrotic material are transported to the blood vessels, and especially the microvascular system is influenced. And here let me just mention, they are running around a lot of mathematicians claiming that they can model the microvascular system well enough. I don't believe it. It's very complicated structures which we have to study more precisely in order to understand those effects. But it's a different problem. A virus attacks also the vessel walls and destroys especially endothelial cells and the epithelial cells of the alveoli. Alveoli are these sacs which have all this above. Inside is the air, and on the surface is the are the capillaries, and then the exchange of the gas goes through this layer. And this is something very, very important for mathematics in this field. Is a lot of these structures, this type, come up all over in the body, are always repeated. And if you look microscopically, you have almost very similar situation. But we are not interested in microscopically. We are interested in what happens in the body, up in the organism. We have to upscale that. We have to get this information from the microscopic up to the macroscopic, going through a mesoscopic situation, and that's one of the main challenges which leads a lot of mathematics. I show you this formally in this picture. Again, you see here the lung, here you have the heart and the tissue, and now the blood vessels. And you can imagine when this exchange of oxygen, replacement of oxygen by the system is disturbed. Open question, I really do not know what happens with the CO2 in the body. I do not. I asked and couldn't find, but good enough. But O2, we know quite well. If there is missing oxygen, then it automatically creates a terrible reaction of the, sometimes terrible reaction of the immune system, because it can get out of control. And where in the body does a virus especially like to be? Nowhere it can talk. There are some indications that they may talk on other places, but preferably on ACE2. If you ask someone who has blood pressure problems, he knows that. He takes medicaments in order to that. And this can create, some of the medication can create more such, lead to more such production of places where the virus can attack. And there's a ACE2 is found on the surface in the airways, lungs, hearts, kidney, intestines, and blood vessels, and some people also know this in the brain. And also the virus can come there. How it goes to this, it's not really good understood. If you want to make a model, one has to know that better. Now let me say something about hypoxia. The hypoxia, the supply of oxygen and energy are crucial factors in the immune defense. Very important. Crucial factors regulating the immune defense. Hypoxia is depending on the state of the process. An inflammatory inflammation activating factor and an inflammation inhibiting factor. In the beginning, when we have created this hypoxia in the lung, then it activates, because it gives the signaling. The body reacts by sending out signals. I have a problem. In fact, we will come later to that point. It produces a factor which is called hypoxia-induced factor, HIF factor. And this HIF factor regulates a lot of things. I'll just show you afterwards the networks. All this can be studied by systems of differential equations. Ordinary differential equation, if you just look at the chemistry. If you want to look at the spread and in the body, it gets very complicated, because you have to put in the flow, how it's transported, and that's not easy, because we know blood flow is not so easy, and also lymph flow is not so easy to describe. Now, they can contribute, if it's activating, to hyperinflammation. That means these people get such inflammation that they don't survive. And the opposite can also happen, which is not so much puts a finger on it. But our specialty is that immunosuppression, it happens too. That means suddenly the immune system doesn't awake anymore, especially it hits the T cells. Again, a problem, mathematical, a problem of chemical reaction system and transport system of the immune cells, and with their interacting with the environment and the influence of the missing oxygen. And the pathological effects are the basic of for the biophysics and the biochemistry. It's the functioning of the cells, their energy supply, and the microenvironment of the cells, the network of coupled processes in the organism and in the system. I show you down here how a simple equation, which is very simplified, showing how the use of glucose, not using oxygen, but there's another way of producing ATP, which is the main fuel for our energy. ATP produces, it can be done without oxygen, but then it produces something which is called lactic acid, and lactic acid changes immediately the environment, because it creates, for instance, that swelling of the cells, and I show you such. It can be modeled, and we did that. You have a cell, and if the concentration of lactic acid inside the cell is too large, water tries to go in. This lactic acid cannot go out. It tries to go in, and that's then things by osmotic pressure changes. We have there outside a Stokes equation for simplicity. We do not assume that there is a supply of water in it coming out from in addition. In this case, then we have a BO equation describing the complex structure inside. Its BO equation describes poroelastic media. And then you have inside the transport of some substances, which the system would like to make less dense, the substance. Therefore, water comes in and therefore creates an osmotic pressure on the boundary condition. You have this balance between the mechanics of the boundary and the situation inside and the water outside, and you have an additional osmotic part in it. Already the derivation of this equation is a non-trivial mathematical problem, which is not totally solved. And it's more phenomenological assumed. And there we have the simulation of a swelling cell. You see, it goes, we took different shapes, and the cell swells, it grows in volume. So tissue does not grow because it's just because of conservation of mass. And sorry, conservation of mass. And then as you see here, what is missing is, if it's growing, the tissue doesn't grow, it just puts more water inside the cell. But if the blood vessels also feed in flow, then the whole tissue, water, then the whole tissue, which is not yet done, but could be done now mathematically and also numerically. It's an open problem. It's a very, very important open problem. Now let me see. Hypoxia changes biophysics and biochemistry. Here I show you some results. That is high efficiency microscopy, which also could be used to discover the virus, but which I will mention later, but it's very expensive, such machines. If you have hypoxia inside a nucleus, the chromatin, which covers the chromosomes, is getting stiff. That means the information of the genome is to the outside doesn't work anymore. On the right-hand side, you also see the studies which have been discussed, done in Heidelberg, that how the structure of the internal network structure is changed. You have this inside fibers which keep things together. And here you see something very interesting. You can do in an experiment down there here, you can let them grow, fibroblasts grow under normoxic situation is left and hypoxic. And this kind of structures we saw before are the situation in the lung by the virus. Can you remember? It just started to put this philopodia, or what they are called. Produce it. It's an effect of the hypoxia, which also can be okay. I said this already before, that we can have inflammatory and anti-inflammatory reactions, and here is this important factor HIF. It's the device of the body to fight the danger of having not enough oxygen. But it creates a lot of reaction, a complex signaling network, which has to be modeled and computed and controlled. Always these problems which you usually have, parameter identification, all this stuff comes on. And this is very important to get involved in this analysis of such systems. And I probably show you that in the next slide, just as an image. Here you have hypoxia. There exists a HIF alpha and a HIF beta 2, which is just one part. And you see all the effects this product has with different kind of signaling. It influences the metabolisms in the cells, the metastasis, the apoptosis. It influences blood vessel formation and production of NO. NO is important for the dilatation of blood vessels, and ROS is terrible for the situation. But here this is influencing it. ROS influences is reacts with HIF, but this comes from as a byproduct. If the oxygen respiration doesn't function well enough, then it produces ROS, which is terrible, poisoning the body. Hypoxia in blood. I said it also already. I can maybe overgo that. No, this is in this part. I have to do that again. The transport through the vessel wall is very much influenced by this hypoxia, and therefore it also influences. Hypoxia also influences all these coagulation process is depending. Some factors are depending on hypoxia, or if there is oxygen or not. Cytokine storm. I said it already before, therefore I can probably overgo that and take more time. But there is, so far, they are mainly, also our medical colleagues were mainly looking at this cytokine storm creating more and more infection, more and more inflammation. And this could not be stopped and can kill the patient. But it's hyperinflammation. But the other side is, as I told you, is already as important. In the next slide, I show you just some of the products influenced by the HIF produced by the hypoxia-induced factor. Don't look at the name, but look at what they influence: cell growth, proliferation, differentiation, motility, survival, and intracellular trafficking. Next, proliferation, gene expression, differentiation, mitosis, cell survival, apoptosis. These are important factors. If they get in disorder, the whole system is getting in a dangerous situation, which finally might get to irreversible breakdown of the whole system, which we want to understand using mathematical models. Here it says in the B cells, this factor goes directly to the B cells, which are very important for the production of the antibodies. And then we have the other situation. We also can have immune suppression, and this is what we just are looking at. Here I have it collected. We have in an image, you see, we can have something inflammatory, something anti-inflammatory. It can go on the level of the cells. Here you have, which an important part is a mitochondria, because that's an energy plant of the system. And we are doing mathematical modeling of this mitochondria. And then cellular differentiation, motility, apoptosis, functionality, epithelial dysfunction. That's now on the level already of layers and tissue. And then finally, here you also have activation of the and coagulation. And here it's very important to look at two parts. I do not know if I will see it just coming just now. Yes, I will come to that in a second. And then we have dysregulation of the supply network and dysregulation of the immune system. It creates disorder in the large one, and some of them can start a vicious cycle. That means you have some problem in the heart. You only can solve this if you get support from the kidney, and if the heart is not working well enough, the product cannot be put up by the kidney from the kidney fast enough. Then it gets less active, And then this also influences the regulation in the kidney. You get in vicious cycle. It sometimes are not reversible, and we can try to do this in mathematical model. I show you now the processes of the endothel, because we did some computations already, that some models. What you see is a scheme up there in this corner up there. You see the cross section through a vessel wall of arterial vessel wall. On the top here is the endothelial layer. That's a very, very important one cellular layer, like this one. But this controls, it's like it controls what goes in and is let out. And this must function. If this doesn't function, the whole system could break down. And the next layer is where all the muscle, it's called media, where the muscle cells lie. And the other part is adventitia, where the supply, they also have to get a blood supply where it's taken care of. But this small layer is highly important. And I showed you several of these epithelium, or they are called in other parts of the body called just epithelium, but for the vessels they are called endothelium, for the blood vessel endothelium, and they get different structure, and according to the different structure they have different properties. When you see here, especially those epithelia, which are, for instance, in the lung and the bronchium, they are different. They also have slime up there and hairy structures, and also in the intestines you have a similar situation, and you have to describe this part of the transmission of substances between these different separated different domains. And here you have a bronchiole. Here you would have no blood, here would have air, and you see again this essential layer is very important. And this epithelial layers all have ACE too, sitting there, and they are marvelous for the virus to attach to. Here you have them. You see, this is in this case not from the lung, but from the kidney. And you see here the virus down here and also here. And here you see these particles. You know it already from other situations. But these are now coming from the kidney. And you have it in the liver. It's not much reported, but they are, I'm sure they are there too. Wherever it can go, it goes. Here I want to tell you now how can we do mathematics now with that. Now, I already said you what is very important to understand these layers separating, for instance, alveoli from the blood vessels, or in kidney you have their blood from the part which throws out all the urine, have a different separation. But you have there, here, the red is blood, the blue is the gas in the alveoli. You have here endothelial layer, epithelial layer, blue. You have an endothelial layer here, because blood vessel, and some structure in between. And now you have here blood flow, you have airflow. And then you have the chance to move from one side to the other side. And here the black parts are the viruses, which like to especially to destroy the endothelial and epithelial layers. And describe, what would we like to know? How does the permeability change? How does it influence the exchange of gas? That's the open problem which we have to do. And we have to model this on this micro level carefully, and then try to scale it up, because we want not to, you cannot compute this. You only can compute small pieces, use this information for in the coefficients of the upscaled equations. And that's what is our aim, and we are just working on this. We have very well studied only this situation. Here, endothelial layer on one side, on the other side this, not these three parts, only the red part and half of it, and no virus, only blood cells of the immune system. And I'll show you. Modeling is the process relevant for the functions of epithelial layers and on nano and micro scales, passing to scale limits, including systems with different scales in different compartments, scale limits leading to dimension reduction. It's passing from layers to interfaces and derivation of transmission conditions, passing from discrete models to field models. And here your colleagues already asked, what do you do with a virus? Viruses are particles, like particles which you look then in the last of equations, no? Particles. And how can you show how they behave there? You have to take particle limits too. And some of these guys are rolling. This is a very complicated problem, how to model rolling. I do not say that that the virus rolls, but the monocytes is rolling. And it depends how well they can roll and the adhesion factors which have to be taken into account in order to control this process. And we need analytically and numerically description of transcellular and paracellular transitions too, because they just do not go just through holes, they also pass through the cells too. And we need some derivation of PO-type equations for the complex geometry, which I showed you. We need to derive poroelastic properties of this material, which is under attack of the virus. Blood clotting. Okay. I mentioned that already before, that it happens. And therefore, I just don't look at the other part because I have already mentioned that before. Various pro-inflammatory stimuli can promote thrombosis by inducing endothelial expression of tissue factor, interacting with the circulation coagulative factor 7 and triggering coagulation. What does it mean? Usually you have coagulation. One aim is to close wounds in your vessels. Since the system has to give a signal that there is a wound. Now, if the virus has hurt the endothelial layer cells, it's opening up. It comes the tissue factor which says there's a wound, and therefore it starts a process of coagulation. Then HIF1 alpha, this factor which I told before, which is in defense of the immune system, an important factor. It downregulates the protein S. Protein S is produced in the liver, which makes the blood more fluid. In fact, it doesn't allow, it's against thrombosis. And if it's missing, then the thrombosis is enhanced. Virus replication endothelial cells causes micro damage in the vessel wall. As a response of the body, the von Willebrand factor releases von Willebrand factor into the blood, which creates more adhesion of and that means it really creates which can get a cascade of clotting and kills the people just by infarct wherever it is in the body. And we have done some simulations already before, very some times ago. It shows you this is thrombus formation. It just shows you, just look at this. It's a complex, but already reduced complex system of chemical reactions, but also chemical reactions of particles which are transported in the blood flow. And what also you have to take into account, also this depends on the shear stress. This reaction very much depends on the shear stress. Here you have the system. You activate you have the platelet inactive, it gets activated, and this is it's enhanced the activation, and then they form close to the wounds, they form such bulks, which are covered by fibers in order to clot to close this bulk. Here you have the system of the also very much reduced system. We just took platelets, active and inactive, thrombin and prothrombin. They are substances which create enhance the clotting, and the C-ACT protein, active and inactive, is again hindering this clotting. And we did with the free boundary problem. There's a complex system of boundary conditions, but that's easy to understand, but we don't have to time enough what are the relation, because on the wounded band you get the information that there is a wound. On the healthy band you send out stop clotting, and then you get this kind of transmission condition. And how you see the simulation, we did it already quite a long time ago. But probably we have to go now in again, but under the aspect that we have the virus inside. And here you see the equations which we finally solved without shear stress. Why? Because the shear stress didn't, the situation could not be covered by the theorems we need all for the Navier-Stokes equations. It's the regularity theorems are not good enough. There's open problems which is related to the research of Solonikov. Open problems. They are not. We need regularity and so on. So now, what is very important? The vein is mostly are attacked, especially in the lower limbs. There, why? Because you see already the structure is a little bit different than you have here. These valves, and the structure of veins is different from that of arteries, which I showed the pictures of an artery. For the vein, I have not available any kind of this stuff. And there the clotting is even worse because the flow is less. The flow speed is less. And therefore, also shear stresses are different. And therefore, we have a different kind of disease then coming up there. So this is we can have already told. Now let me go what we did just for the inflammation. We looked at just the immune reaction, and this paper, which is just came out, it was already a longer time in discussion with some referees who had not very much knowledge about the processes behind, and but finally it's published, and it tells you how the changes are that the monocytes, which are the important immune cells, they have to go to the tissue in order to fight the pathogens. And then we had set up a model for that with all complex. It gives up a huge complex system. Here you see it once more. You see these monocytes are transported in the blood, they roll there, they penetrate, and then they get macrophages, they form foam cells, and the foam cells start to swell. And the processes afterwards we could not model, we just looked at the first part, because then after in the next step, the muscle cells are coming, and we looked at, this is lipoprotein LDL, which is an important factor, and all this, and put it together in a system. They finally form, it swells, the swells in fine plaques and ruptures. And if the ruptures come, then the material goes out and blocks somewhere else and leads to infarcts in the body. Now let me just see here. We did the following. We took Navier-Stokes equation for the blood flow, Bio equation for the poroelastic vessel wall, convection and chemotaxis of substances, like I showed you, immune cells and LDL, oxidized LDL, and so on. Reaction diffusion equations for transport signal and action of processes that trigger the inflammation. And but we focused on the role of the endothelial layer and the intima, not the next steps. It's only the first part. And this just appeared, you see, here in July 7th. It was in Journal of Theoretical Biology. But this system in this paper, this computation which I show you, have not been contained. Only not the growing part and not the flow in the wall, which was too complicated to do that. And we did, but now we did in the meantime. What you see is we started from a hump which existed already in order to have some shear stress. Then you see the flow features around the hump, normal hump. No, and then you see here coming up after a certain time, coming up a second hump in the vessel wall, which finally could block the whole vessel wall, so flow. And here is a huge system. I do not want to get into it. In 3 compartments, in the blood, on the interface, and in the vessel wall itself. And this is a huge system of differential equations. And here you can see the results, which we can get by in time. LDL, this was an important factor, which you all people know in arterial sclerosis, a very important factor, LDL. And then you see there in time there's also an oxidized LDL, and you can follow up how it transports monocytes. And monocytes, here you have the chemical substances which is created in order to signal. And then we have the changed monocytes that are macrophages, and you have here foam cells finally. What you can do, you have now a digital experiment to try to study that. And the problem is, again, as you said, we have to look at validation. Now I also want to go and look at one important part. It's the oxygen and energy supply and the dysfunction of that. There we have to study what happens in the mitochondria. And you see on the left-hand side, the mitochondria, and inside a huge oscillatory part where all this is very important for the, especially for the oxygen-based respiration. And you have a cytosol outside. If it's not oxygen related, then this is not involved so much. It's mainly outside in the cytosol stuff, and you see all this. It has two membranes, and there's an inner membrane which is very complicated, and an outer membrane which is less complicated. But we have to study now all the chemical reactions in such a situation. And here you have this again. And which is very important, there's not just ODEs involved, normal ODEs. There's a build-up of an electric potential which is necessary to transport the oxygens to the place where it should be. And we set up such a system. You have glucose can go the oxidized way, and can be produced in oxidative respiration, and it produces 34 ATP. Whereas if you go via the anaerobic, then it creates only 2 ATP in the balance. That means a high difference, but you can see the effect. And we did this. I show you just one of these systems which we had to set up. It's a reaction system. This is the anaerobic and how it is coupled with the aerobic. And you also have a digestion or use of fatty acids, especially in the heart, to produce all what we want, ATP. And it's controlled up here by this factor HIF factor 1. It's a very complex system, but we have to understand this in order to understand the main processes in this inflammation in general. And we did it for a reduced system, and it just came out again in June. It's a joint paper of Bocharov, Knoch, Maria Neuss, and Manfred Thiel. He's internal intensive care medical part, and it's called Mathematical Model of HIF, Regulated Cellular Energy Metabolism. And it's a system of ODEs. And now if you have that, you can compute all the species which you are interested in. I put you some of them. Main thing is glucose and ATP and lactic acid, and the others are some enzymes which are needed for the production. But you can now do experiments on the computer which you otherwise could not do on. This is production of ATP independence of O2. This is very important for us because we finally are not so interested in the process. We are interested, if you have a known number of O2, how can you get this back to, how can you, do you know what is ATP production? And you can really make in a, what some people usually also call a digital twin, it's called in industry. You have a machine which you can feed with data, and it tells you, puts in this data, takes it for parameter identification, for instance, and produces then the outcome of such a unit which you are interested in. Here I show you a picture which will trouble us in the future very much. You see essentially such a triple layer, such a layer part which we saw before in the situation of the lung, is a section. Here, look at here down, it's a little bit better. You have one side, there is the liquid which should get out of the body. On the other side is a blood. And you have cells in between which control the transmission of that. Here you have the endothelial layer, epithelial layer, and here you have a membrane. And here you have the virus. The virus likes to sit where, you know it already, ACE is, but there is ACE. And therefore, in the kidney, in very small units, there are millions of that inside the kidney. We can try to set up a model for a small unit and scale it up and try to get some result for the kidney, which is a very important stuff. Yeah. Yeah. Now, specific features and challenge to modeling and simulation control of a virus sepsis. COVID-19 develops as virus dynamic under certain aspects differently. Put proliferation process of the virus more in the focus of the model development. To the fact that the virus is hitting the lung early and rather severe, hypoxia and the cytokine production get out of control more frequently. Processes are getting more complex. You have not to be afraid of complex processes because they are complex. Otherwise, it's not a topic for your for research. You have to try to reduce complexity. It's a very early start of clotting, the strength of this process and the strong increased incidence of infarcts in blood vessels of all scales attract more attention in modeling. The complex profile as SARS-CoV-2 requires a more detailed analysis of the basic process, delivering information needed to better define and quantify, like transmission, immunity, incubation time, and serial interval infectivity and its duration, and the lethality. And what is very important, try to help to set up tests and vaccines. They should be efficient, available as soon as possible, and affordable for all, are hard to achieve. All of them is not easy. Mathematical and computation expertise and methods can support. So, I show you, yes, I'm finished. Yes?
We have no time for...
No, it's just,
it's about...
it's in 1 minute, I'm finished. I have exact time. And it shows the immunoglobulin, and that I said already before, we have to understand better what happens with the P and D cells, and we should not take just only the model from the last century. Here's the microscope structure, which are too expensive, but you see the super light microscopy, but there always we can help, and then we are finished. I think we had it already. I had it already said before. Okay, that's the next lecture is coming then tomorrow. And it's now in our term 11:45. But this is already the next lecture.
Thank you very much, Professor Jäger. And we have some questions, and some of them are from the previous lecture. But is it possible to take into account the mutations of the virus in the mathematical models?
The problem is, first of all, we have to find out. We have to find out what is the probability of mutation. And there's a study of Bob Benner is very much going in this direction, because mutations means which part of the, for instance, of the glycoprotein can be changed easily, because it's an important part too. And also the mutations of the genome. And if you want to say, if I have a mutation, how does it affect the process? This is a very hard problem. Because even if we know this situation, how can we see how the mutation affects all the chemical processes? That means it asks more than what we have problems now for years with our situation. Therefore, it's difficult.
Thank you for your answer. Is the beginning of epidemic, Germany had less death cases than other European countries?
Excuse me?
In the beginning of epidemic, Germany had less death cases than other European countries.
I usually looked on this situation quite carefully. I mean, the problem is, first of all, you have to not only to compare the epidemic spread, you also have to compare the hospital system. And I think we should discuss that in the last lecture, because I will show you in this lecture which some of you may like. In October 2019, there was a publication of an index predicting how good a state is prepared for such an event, disastrous event. And I tell you, you will not expect, maybe you expect the results, but it shows that all these indices were all of no use. We can discuss this next time. But what you see very strong, less deaths means probably the system may have be, if you compare it to other countries, it could be a better health system, but also not believing in herd immunity. Some countries believed in herd immunity, and don't be astonished that they have more deaths. Look at UK, look also at Sweden, and I will also tell this on the next lecture. But already you see, comparing the situation in different countries is very complicated. Why? Look at Sweden and look at Germany. Sweden, I think, have about 1/10 of the population or something like that, like Germany. But they also have a different concentration. And you see the structure of the spread very much depends not only on the pure geographic, it depends on the commuting, how people commute between. It's very complicated, and I blame those people who use models which do not take this into account, because the predictions are throw a coin. Okay, not more.
Thank you very much. And the next question is, because of the urgency, won't numerical methods and data analysis supplant theoretical mathematical approaches?
Excuse me? What?
The question is, if the numerical methods can substitute theoretical mathematical approaches. In other words, should we work in a hurry or take the time to understand?
No, I think you cannot separate it. You have to understand, you have to understand and also compute. And let me just warn you very carefully, and I'm on a side with some people who are coming from numerics. If you do numerical systems reductions, you may destroy the interpretation. And that's not good. You have a better numerical result, but you don't understand it better. You may have it faster, but you have to combine both of it. But you should be willing. It depends what you do. If you do, for instance, a study of blood flow, as we did, you need really the best what you can get in, let me just take the name, ALE methods for problems with interactions of flow with a moving boundary. But you also may need more, if you want to look at the spread of an epidemic. I think don't use PDE, because the PDE will not give you what you have to study. There is no, you will see it tomorrow too. I show you a picture of the data in a really dynamic situation of the spread of the in the east coast of United States. These are not diffusion equations. No, not at all. They are essentially network system. It's processes on networks. And if you want to replace it, you better do integral equations, than diffusion equations. We studied the spread of the rabies. We studied maybe 30 years, 40 years ago, with using integral equations, because then that is not a diffusion process. That's not simple diffusion. Not at all.
Thank you very much. And one more question is it possible to use the Vlasov type equations for describing of some processes? For example, to describe the evolution of the density of the infected cells?
I would like to discuss that. I really would like to. I think there is something where we come together because we have many particle systems, okay? And moving also under influence of forces from the outside. I think there's a chance, but I don't say that the Lazarev equation will be a result. Usually those kind of systems are not ending up have not a generator which can be represented just by a PDE. It usually has functional terms in it. I can show, if you are in fact, let me ask you, if someone really wants to more detailed information, I'm willing to do that. You have my email, write me a letter what you are interested, and I have a huge collection of what I could get hold of. You know? But I think it's necessary to look at this together. I mean,
thank you very much.
This kind of interdisciplinarity is very important for us because our methods as mathematicians are transportable very often. But usually you cannot use exactly the same. You have to make changes. Let me just mention something, and then I stop. Is the fact that also people from economy and finance are interested in epidemiological models. Okay, I'm finished.
Thank you very much, Professor Jäger. I guess we should make a small break now.
Mm-hmm.
Oh, excuse me, we have one more question. It's how to include into the classic compartment models the super spreader.
Excuse me? How
to include into the classic compartment models the super spreader?
I think the only thing what you can do, you have to take let me say, take a network model, and then you can include super spreaders. A network model. Take as a center, you may also sometimes try to get hybrid models, but I will tell that in the next lecture. You should start with more network models, which are closer to social networks, with internet networks, which are closer to economical networks. And I will quote tomorrow a lecture, a statement of a director of a bank. We had 2008 this breakdown, and he says we should go and learn from epidemics because it's crash breakdown of networks, more network structures. Or you could simulate it continuously with integral operators, but not with diffusion. Already years ago, 1976, my student Horst Thieme modeled this in his PhD thesis, all this spread with integral operators. The reason, because the foxes have a certain pattern to run, which you cannot say it's a diffusion type.
Okay. Thank you very much, Professor Jäger, for your lectures and for your answers. I guess we should make a break now and for next speaker to prepare for it. Thank you very much.
Thank you. Thank you for your patience with me. Okay.
Good afternoon, dear
Oh,
listeners.
hi. I'm hearing you.
Can you please share the screen?
Okay, now I try again. I did it. Okay. I go to screen number 1. Now you should see it.
Yes, we can see it. Thank you.
Do you see it?
Yes.
Okay.
Yes, thank you. So our next lecture is Hans-Otto Walter, professor of Justus Liebig University of Gießen, with the lecture Differential Equations with State-Dependent Delays, Some Theory, New Phenomena and Applications.
Okay, so thank you very much. Now let me just go to full screen. Okay, so do you see the screen, the lecture?
Yes, the first slide.
Yeah, okay, so you see it. Okay, thank you. Okay, so let me begin. Now this lecture will be very different from the previous lectures. It will be a kind of introduction, and in particular to those who are not familiar with differential equations with a delay, and in particular with differential equations where the delay is state dependent. The second and the third lecture tomorrow and on Friday, they will present new phenomena, new material, new results. But this first one, this is very basic and introductory. So let me begin with what may be called autonomous, retarded, functional differential equations of a classical type, where you have delays in an equation, but they are fixed. And what you see here, these references are the, let's say, latest major monographs in the area, which cover these classical equations. So here's an example. Here, the equation you see is scalar. The g is just a real function, and h is fixed. It's a positive number. That's the time lag or the delay in the system. A general form of these autonomous retarded functional differential equations is what you see at the bottom, x prime of t equal to f of x sub t. The f goes into Rn. And in this equation, the x sub t is the history of the solution at time t. What does that mean? You look at the solution over the interval from, say, t, which is now the present, back to t minus h in the past. You take this piece of the solution and shift it back to the interval from minus h to 0. And these pieces of the solution, shifted pieces, represent the history of the solution. Usually or often I call them just segments. And now the f here is defined on some general open subset of the space of continuous functions on this initial interval from minus h to 0, and the map goes into Rn. We can rewrite the example in this general form if we take the f of phi of some function on the initial interval to be the real function g at phi at minus h. If you replace phi by x sub t, then you recover from the general form the initial example. And in that case, of course, u is the whole Banach space C, and the n in the Rn is just 1. What is a solution in this, let's say, classical context? It's a continuous function which is defined on the interval from minus h to some positive te, which could be plus infinity, and it's required that x is differentiable only for positive t, and there for such t it should satisfy the differential equation, of course. And here you see the initial value problem. You prescribe some function phi in u, and you ask for solutions as above, so that the initial segment of the solution, which also is the restriction of the solution to the interval from minus h to 0, coincides with the prescribed initial function. And then this initial value problem is well posed in the sense that solutions do exist that they are uniquely determined by their initial data and that they depend continuously on the initial data. In this sense, the initial value problem is well posed, provided f is, as an ordinary differential equation, let's say locally Lipschitz continuous. And then if we denote this unique solution, uniquely determined by the initial function, by x uppercase upper index phi, okay, then we get a semi-flow. That is a map which is defined on t non-negative and phi in the domain of the nonlinearity of the equation, and it assigns to this pair t and phi the solution segment at time t. And as you see there, this f is locally Lipschitz in case of the example, if only the g is locally Lipschitz. Actually, one doesn't need, for the example, g to be locally Lipschitz. Continuity is sufficient. One can use some elementary method to construct solutions which are unique even in that case. The nice thing in the classical situation is that the solution operators, the time t maps, you fix the t in the f and let the phi vary. These are as good as f as far as, say, orders of continuous differentiability is concerned. That means, for example, if the f is continuously differentiable, that you have a principle of linearized stability, for example, which is the, well, most important tool as far as applications are concerned of analysis. You get local invariant manifolds, all the tools from dynamical systems theory you can use in order to study examples. Now let's go to equations with variable delay, state-dependent delay. What is different? Well, let's begin with an example. That's the equation number 2. The g is as before a real function, but now the constant time lag h is replaced by a delay functional little r, which assigns to each state, let's say in the space C, continuous on the initial interval, a delay, non-negative, but with an upper bound h to make everything consistent. We can also rewrite this equation in the general form of an equation as in equation number 1. For the f, you only have to take what you see at the bottom. You take f of phi to be g of phi evaluated not at the fixed minus h as before, but at this state-dependent delay minus r of phi. And again, in this example, u, the domain of f, is all of c here for a minute. That will change later on, by the way. And the n of the Rn in the definition of c is just 1. Well, let me spend a few minutes to present another example. The first one is a bit artificial if you think of possible applications. This is a very simple model, a very basic model for what may be called automatic soft landing. So think of a vehicle which moves in vertical direction. It wants to go down to the ground and wants to land there, and it should not land in a crash. So U, non-negative, describes the position above ground. Then the vehicle sends a signal to the ground. The signal is reflected, and the vehicle senses the reflected signal and measures, it knows the signal running time, the time the signal needs to go to the ground and back. And from that signal running time, it uses a formula to get a position, which in general is not the true position above ground. And then it uses this position to react with a certain response, acceleration or not, in order to continue to move downward. So here are the equations. The first equation is the signal is an equation for the signal running time, depending on where the vehicle was when the signal was emitted. That's time t minus s, and where the signal is now at u of t. And then the next formula, you know, the signal went down and went back. So one takes the average and computes from that something which is taken to be the position. It's the true position only if the vehicle is in the same position when the signal was emitted and when it was received. But that's all the vehicle can do. It has only the signal running time. From that it has to make a guess about its position. And then we have Newton's equation, which you see at the bottom, but you see in the acceleration term, the arguments are the computed position via the signal running time and some expression for the velocity at the vehicle at time t. Well, let us assume that the signal is not too far above ground, so you have this inequality up here, and also that the motion of the signal is less than the speed of the, the motion of the vehicle is always less than the speed of the signal. Define a maximal delay by this formula. And then the equation for the signal running time looks like this. Now it's written not with a possible solution, but with the first component of a state, of the phi. And we assume that phi is continuously differentiable, and also phi corresponds to the positions that it's bounded by b. And then this equation that the motion of the vehicle should be less than the signal speed of the signal means that this equation, which you see up there in the second line, that this can be solved by a contraction. So the signal running time is a function of the state, of the positions in the past, the history of the positions. Now we try to rewrite this set of 4 equations in the general form 1. So we have a pair, the phi corresponds to the positions and the eta corresponds to the velocities. And then what you see, the f1 of psi, this is only the first equation of the system rewritten with these components phi and eta of the state. In the second equation, you see here the a, the acceleration. Here this is the p, the position computed or guessed from the measured signal running time. And here we have to insert something for the velocity. Well, if you base, what should we take? If you base it on the speed of the vehicle, the vertical speed, and you look at the formula for the speed when the system is moving, then you can come up with this formula, but there are other possibilities. In any case, what are the questions? What should this model answer? Soft landing means that the U is always above ground, the first component of the solution, and that at some instant of time we are on the ground, the U is 0, or we should also allow asymptotic soft landing where the U goes to 0 and the velocity also goes to 0 as t goes to infinity. A crash, on the other hand, would be a situation where the U is 0, we are on the ground, but there's a non-zero vertical velocity. Yeah, and this should be avoided. And then a problem for the model, the first thing one should do is one should try to find initial conditions for soft landing. Is there an open set of initial conditions which produces soft landing? Okay, so much about this example. There are many more. At the bottom you see a survey article which is not new. You find all reference to all these applications in this survey. Let me just mention that this two-body problem of electrodynamics, which you see up there in the second line of the examples, this is by now more than 100 years old, and still it is very little understood. Okay, I'm still a little bit after my time, so let me switch to the next one. Well, the first basic questions now for the equations for the state-dependent delay. How is it with the well-posed initial value problem? And it is here where the theory which I'm going to present, which I'm going to introduce, differs from the classical theory. And let us see why this is so. Let's go back to equation number 1 in case of our example with state-dependent delay. Then the first question is, how good is f? Are there some local Lipschitz conditions or so? Well, this becomes clear if we rewrite f as a composition. First, you see we take the phi and the identity, we keep it in mind, and we apply the delay function of the minus r of phi. and then we evaluate the phi at minus r of phi, and then we apply g, as you see it above. Now this EV, this is the evaluation map which assigns to each pair a state and C and a time in the initial interval the value of the phi at S. And this is the bad guy in the whole story because it's only continuous, not locally Lipschitz. The situation improves if we go to a smaller state space, the space of continuously differentiable maps on the initial interval. And if we restrict our evaluation map to that space, times initial interval, of course, then it becomes continuously differentiable, and you can compute the derivative. That's a linear map at given phi and S, and it operates on H's, which are in the space C1, and U in the initial interval, and there you see the formula. And what we should notice here is that this formula does not involve the derivative of He. There's no He prime, yeah, and this will play a role in the sequel. Now, if G and the restriction of the delay functional to C1 are, say, continuously differentiable, then the chain rule tells us that also our functional on the right-hand side of our equation is continuously differentiable, of course, with respect to the norm or topology on the space C1. And here you see a formula. The only thing which we should observe here is that, again, in the formula for the derivative of the right-hand side, the functional which determines an equation, we do not see the derivative of He. Yeah, this is important. Okay, this is just by the chain rule. Now, at this point, one might think of a well-posed initial value problem for our equation number 1 in general form on open subsets of the space C1. Well, now let's generalize a little bit. Let's forget about our particular example. Let's assume we have an F, the right-hand side of the equation, on an open subset of the space C1, and that F is continuously differentiable, as we could achieve just a few minutes ago. Now, what does that mean? If we have a solution of our equation number 1, then you see that all the segments of the solution belong to U. U is in the space C1, so that all segments, all restrictions of the solutions to intervals of length h are continuously differentiable. That in turn means that the solution X itself, on all of its domain from -h to dE, is continuously differentiable. But being continuously differentiable, it follows that the curve of the segments of the history in the space C1 is continuous. That's an elementary exercise. But having this continuity, we can pass to the limit at 0 in our differential delay equation. This is what you see at the bottom. So you see the derivative of x at 0, which exists according to our previous observation, is given by the limit of the derivatives of positive t. They are given by the right-hand side of the differential equation. And now, because of this curve of the xt's is continuous, and the f is much better than continuous in the C1 topology, we end up with this equation x prime of 0 equal to f of x0. So we end up with an equation actually for the initial data. So we cannot expect a solution for initial data in a whole open subset of the space C1. And we are led to consider this closed subset, which you see here, and which one may call the solution manifold. These are those data in the domain of the F, which at the left endpoint of the initial interval satisfy the differential equation. You may call this equation for the phi here also a kind of compatibility condition. Well, how should we think about this set F if we compare it with classical theory and a linear autonomous delay differential equation where the right-hand side is defined on the big space C? Then this equation generates a semigroup on this space of solution operators. The semigroup has a generator, and what you see here at the bottom now is the domain of the generator, which belongs to C1. It's completely analogous to our so-called solution manifold, well, with a nonlinear F, which you see above there. another aspect is, again, if we think a little bit once again of these classical equations where the F star lives on an open subset in the space C and is locally Lipschitz, then if you look at solutions and you wait a little bit, time larger than the maximal delay in the equation, the h, then these sets x sub t, they are continuously differentiable, so they're in the space C1, and the differential equation is just the compatibility condition. So if you wait long enough, the solutions of the classical case, they end up also in the solution manifold, which means that the solution manifold contains all stationary points, periodic orbits, all long-term dynamics of the equations. So it's certainly an object which also for the classical equations is of interest. Well, how good is XF? XF is defined by an equation. So it looks as if it's say a closed subset of an open subset of the space C1. Well, but what we want to do is we would like to get a well-posed initial value problem on the solution manifold. And in order to get that, we need that the solution manifold is not just a closed set. We should have some differentiability structure on it. It would be nice if it would be a manifold, a differentiable manifold. And for that, we need an additional hypothesis on F. And here it is. You see the derivatives of F at phi in U, they are continuous linear maps from the space C1 to Rn. And now this additional hypothesis requires that each of these derivatives has a linear extension to the bigger space C. This is the D sub E of F at phi, which you see here at the bottom. And then, in addition, the hypothesis requires that the map which you see now, that this is continuous. You take a pair, a phi in U, where the F is defined, where you differentiate it, and a chi from the bigger space C. And then you apply the extended derivative at phi to chi. And then it's required that this map is continuous. This is very similar to what many years ago had been introduced by Maliparenus-Baum and Paraskivopoulos into the theory of delay differential equations with state-dependent delay. They had a notion called almost Frechet differentiability. It's a little bit different, but it's similar. A few comments. First of all, this hypothesis, which I just showed you, it's mild. In the example and in the soft landing system, it is just the fact which I emphasized, that the formula for the derivative of F does not the real derivative on the space C1 does not involve the derivatives of the chi, which you see here. That means in order to define your extended derivative to the space C, you can use the same formula as we had it for the derivative of F. You just can use it for chi's which are only continuous. Secondly, these extended derivatives, if they exist, they are unique. And finally, people might find it more natural to have a condition like the one which you see now, namely that if you assign to each phi the extended derivative as a linear continuous map from the space C into Rn, that map is continuous. But if you try that, you look for applications, equations for the state-dependent delay, then you understand that this hypothesis, which is only a bit stronger than the one which I showed you before, is too strong. It's never satisfied if you have equations with a state-dependent delay. Let's begin with results. Now, first of all, about the XF. If that XF is non-zero, well, that is always the case if you start with a decent delay differential equation, then under this hypothesis, it is true that XF is a continuous differentiable submanifold of the space C1. It's infinite dimensional, and the codimension, the missing dimensions, they are n. This is, so to say, the number of the equations if you write the equations as a system. The F on the right-hand side goes into Rn. Let me say a few words about the proof. Well, let's look at the situation. The n is 1, the u is all of C1. Then the set XF, by definition, by the equation, is the zeros set of P minus F, where P is just the projection, no, it's the evaluation of phi in C1. We take its derivative and we evaluate at 0. This is linear continuous. Yeah. And then we want, in order to get that XF is a submanifold, we want to represent it locally by a graph. In order to do that, we would like to apply the implicit function theorem. Now, the implicit function theorem, which yields a graph representation of zero sets, has a hypothesis, namely that a certain part of the derivative is a topological isomorphism. If we know that all derivatives of this P minus F are onto, then we also know that the restriction of these derivatives to a complement of its kernel, it's a map which goes into from a one-dimensional space to the one-dimensional space R, that this is a topological isomorphism, so we need the surjectivity. How do we get it? Well, here you see the formula for this derivative at the after the last equal sign. You see x prime of 0 minus, well, we can take the extended derivative of f at phi at t. And the only thing we need for surjectivity is that the map is non-zero, because we are in a one-dimensional situation. We have to find a phi for which this expression at the right end of the chain of equations is non-zero. Now, if we take a phi which in the space C1, which in phi norm, in the C norm, sorry, is small, then also this DEF of phi of phi is small, because here we are in the big space C. But of course, we can choose phis which are arbitrarily small in C norm, but say which have derivative at 0 equal to 1. And for such phi, our expression here is non-zero, and we get the desired surjectivity. Yeah, so it's actually easy, and this can be generalized to the situation where the n is more than 1 and so on. Okay, so much a little indication about the proof. While being a submanifold, then the tangent cones are nice closed linear subspaces, and there you see they are also given by the equation which you get from differentiation. Now, incidentally, since all the rest of this first lecture is about results which are now almost 20 years or better 17 years old, let me briefly also mention something which is very recent. You see the XF is defined by an equation, yeah, but this does not give us any idea what this XF might look like. What's the form, the shape of it? And the very recent result of this year is that in many cases, actually, this submanifold XF can be written as a graph. It's a submanifold of the simplest type, given by a map from a subspace of codimension n in the space C1, a map into some complementary space. For example, if in our example with the state-dependent delay, the delay functional has a positive lower bound, then we know it's a graph. And if the delay functional does not have a positive lower bound, but at least it never assumes the value 0, the delay is never 0, in that case, we get something which is not a graph, but it's something which I call an almost graph. And then one can also show that one gets a diffeomorphism of the XF to an open subset to a subspace like the H which you see here. An example of an almost graph in 3 dimensions, for example, is the unit sphere without its north pole, for example. Yeah. Anyway, let's return to our present introduction. Furthermore, under our additional hypotheses, we get, if we look at the initial value problem for initial data taken from the solution manifold, then that is well posed. We get maximal solutions which are uniquely determined by their initial values. They are continuously differentiable functions right away from -h to TE. Here you see again the initial value problem for initial data in XF. Now let me try to say a few words about the proof. It's oriented, of course, on what you always do if you try to find a solution of an initial value problem. You try to convert your problem into an integral equation and you try to solve that by means of the contraction. Now here, first of all, it would be nice to have a Lipschitz type condition for our map F. And actually one can get one. And let me begin with that, how to get that. From our hypothesis on the F. Again, the Lipschitz condition, which you will see, is something which is again similar to what appeared in this older paper by Malé-Paré, Nussbaum and Paraskevopoulos. There they had something called locally almost Lipschitzian. Now what is that? It's an estimate of this type. Each point in U in the domain of F has a neighborhood n, so that there is a Lipschitz constant, so that you get this Lipschitz estimate which you see. But notice, this Lipschitz estimate is not just the local Lipschitz continuity of F, which you get from continuous differentiability. In that case, you're on the right-hand side, you would have the norm on the small space C1, which is big. But here our estimate has the norm on the big space C, the small norm on the right-hand side. This is much more than this the local Lipschitz continuity of F, which you get just from smoothness. Well, how would we get this thing? Let me just try to explain it. First of all, if you play with this hypothesis on F, which I explained to some extent, and you exploit continuity at phi, this is very differentiate, and at 0, this is the argument in the space C, then you see that these maps D, E, F, that they are locally bounded. And this can be used. For example, if we try to prove get our Lipschitz condition, which you saw just before, then you write down f of psi minus f of chi, all in a small neighborhood of one particular point. And then you can represent this by an integral. And in the integral, you can replace the df by the def. And now you can use the local boundedness of the def. And this refers to the norm of the linear continuous maps on the space C. And that means this local boundedness gives you this estimate, which you see on the bottom with the C norm. Yeah. Another thing, the second little thing about the proof, which I would like to mention in a few minutes, is the following. I just said what one does, as in ODE side, one converts the differential equation into an integral equation. Let's first talk about this. The thing with the key estimate will follow after that. Let's take an initial value phi in xf and some capital time t larger than 0. And let's think of phi being fixed. The first of all is we extend this phi to a phi hat so that it remains continuously differentiable. You see the formula there. That is obvious. And then we write x, think of the solution. We would like to split the solution into a part which is independent of the initial function and a part which depends on the initial function. And if we split it in this way, we write it u plus phi hat, then phi hat is 0 on the initial interval because we think of x being a solution which initially is given by the phi. And now here comes the fixed point equation. U of t is x of t minus phi hat. For phi hat, we insert the formula. And then we can write the x of t minus x of null as an integral over the derivative minus t. Remember, phi is taken from the solution manifold. The phi prime of 0 in the last line is the f of phi. Okay, we continue. We write this as one integral. And then again, we use the definition, if you wish, of u in terms of x in order to arrive at this expression which you see at the end of the chain of equations here. And this is our fixed point equation for the u, for the part of x over the integral from 0 to capital T. And then you see the operator capital A of u. And this operator should become a contraction. And now we come to what I call the key estimate. We should get a contraction. Capital A should be a contraction on the space C1. For that, we need in particular an estimate of the term which you see here at the beginning of the second line of the derivative of A of u and A of v. Think of u and v, both they are 0 on the interval from -h to 0, and then they are given by this formula which contains the phi. Anyway, if you look at the formula defining A, there's an integral. If you differentiate, you end up with what is under the integral. And then the next thing is you use this strong kind of Lipschitz condition where you have the C norm. But now you see the C norm written explicitly. You can estimate it because the u and the v between -h and 0, they are 0. They are estimated by the max of u of r and v of r for r between 0 and capital T. Now here r, of course, is the independent value. It has nothing to do with the r, which was the delay functional before. Sorry for that. But now you can replace the u of r minus v of r. Remember, u at 0 and v of 0 are 0 by an integral over derivative. And then you arrive at this maximal where you see the capital T multiplying the max, not only the L. The L can be large, but now you see if you take the T small, then the L times T can be made less than 1. Yeah? And this is the way in which you get the contraction with respect to the C1 norm of the operator for which you would like to have a fixed point. So this is the key issue in the whole proof of well-poledness of the initial value problem on the solution manifold. Now let's continue with the result. Well, we got these maximal solutions for the initial value problem, and we can use them to form a semi-flow on the solution manifold just using the histories of the solutions given by the initial values. This is continuous, jointly continuous. But if we, and the important thing, but the even more important thing is that if I look at the solution operators, I keep T fixed, take as a domain of my map all phi, so that T is in the domain of the solution given by phi, and then I get a map F, and these maps, they are continuously differentiable. And then say, as in ordinary differential equations, their derivatives, here written as a partial derivative of the whole semiflow, they are given by the solutions of a linear variational equation. This is the V with the upper indices phi and chi. Here you see the variational equation. This is now non-autonomous. You see the T on the right-hand side and the argument of capital F. It's a linear equation. But remember, we are on a manifold. The maps F of T dot, the solution operators, they map open subsets of the manifold into the manifold. Their derivatives, they live on something linear. They live on the tangent spaces. And accordingly, here in the formula for the derivatives of the solution operators, we are concerned with the solution V, which is continuously differentiable everywhere where it's defined. For initial data, only taken in the tangent space of the manifold at the point phi. Back to the semiflow, in both variables, it's continuously differentiable if you take T large enough, T larger than H, the maximal delay in the equation. This is as in the classical situation, and this result is optimal. Yeah, you would not get continuous differentiability of F for T less than or equal to H. One can also obtain a result about compactness of the solution operators, which is good to have if you want to analyze particular examples. Well, you need that the little f is bounded, and then you have some analog to this kind of local Lipschitz condition, which you get from the hypothesis. You need that you have an estimate of the type with a small norm C on every bounded subset of U. Yeah, then you can get compactness of the operators. Finally, let me address some issue which has to do with a method which had been developed before all this theory, which I showed you a little bit of just recently, and which also was able to associate a linear equation with a nonlinear equation with a state-dependent delay. How is this old method related to what I have been showing you here? Now suppose the zero solution function is a solution to our equation number 1. Then what is the linearization of the semigroup at the stationary point 0 in the solution manifold? Well, this is just the family of the derivatives of the solution operators at this fixed point 0. Yeah, and these derivatives, they in this particular situation, they map the space T0 of xf into itself. They are a strongly continuous semigroup on this space, and this is given, as you saw before, by this variational equation, which is now autonomous. It's linear autonomous, but only for initial data in the tangent space. But according to our hypothesis, we also have this extended derivative on this big space C, and we can also consider the classical initial value problem with these linear continuous maps D, E, F at 0, yeah, which defines a semigroup on this big space C. And then our S, our linearization of the semiflow, this is given by restricting the semigroup which we get on this big space C to the tangent space of the solution manifold, which also is the domain of the generator of the semigroup SE on the big space. Anyway, now how about this heuristic method which I addressed a minute ago? This heuristic method says the following: if you don't know how to linearize a differential equation with a, say, state-dependent delay, you could also try the following. You have an equilibrium solution, you freeze the delay, you take the value of the delay at the equilibrium, at the stationary point. Then you have an equation with constant delay, and that can be linearized. You know what to do. And this has been used successfully by many authors, particularly Cook and Huan, in the sense that the linear equation which they get from this heuristic method, they could use this in order to transfer, say, stability results from that linear equation to the nonlinear equation with the state-dependent delay. But it was not clear what the role of this linear equation was. It was not obtained by differentiation. And also, one can apply or use this heuristic method only for equation where the state-dependent delay is explicit in the equation, where you see it. Otherwise, if you look at the general form with the f of x sub t, you do not see a particular state-dependent delay. You do not know how to freeze the delay at a particular point. Okay, let's see what the relation between the heuristic method and what I showed you before is. For the equation number 2, the example with the state-dependent delay, let's assume g of 0 is 0, then 0 is a solution. And the heuristic method, if you do that, gives you this variational equation and this initial value problem. Yeah, the R is taken at 0, you freeze it. But if we do true linearization by differentiation, then we look at the initial value problem number 3, which you saw on the previous screen, for this particular f. And if we do the calculations, then we see that the right-hand side of the differential equation, this initial value problem, is just df of 0 he, and you end up at the right-hand side with g prime of 0, as in the equation up there coming from the heuristic method, times he evaluated at minus r at 0. The reason for that is that in the full formula for df0 at chi, there appears the derivative of the stationary point of the constant function 0, and this is 0. So this is not there anymore. And that means if I, in this equation number 3, which I get from the theory, it is just the same as the equation which I get from the heuristic method. Yeah? In other words, these initial value problem number 3 that generalizes the heuristic method to all delay differential equations with a state-dependent delay, also those where you do not have an explicitly visible state-dependent delay in the equation. Okay, so much about this. I used a little bit more than I should have. Now, thank you very much for your attention.
Thank you very much for your lecture. So, seems like your lecture was clear because we have some thanks for your lecture for listeners, and one question: how can we have the slides of the lectures?
Sorry?
One listener asks how he can have the slides of the lecture.
Oh, the slides. I mean, I think I sent them to you by email, and you can distribute them if you want.
Okay, so you can write on email of workshop and we can send.
Yeah.
Okay.
I think I sent them already to you.
Yes, I just don't know. Do you want it to share with everyone, or?
Yes, you can distribute them to everyone who is interested.
Okay, thank you.
Yeah, you're welcome.
So we have no questions. No more questions. Again, thank you for your interesting lecture. And now we can have a break for lunch till 3 p.m. Moscow time.
Oh, yeah, okay. So thank you very much. And everybody who was listening, thank you very much for your attention.
You too. Dear colleagues, please note that for next 4 lectures you need to use another link and there will be a new broadcast. Thank you.